with two remote talks in the form that we have a pre-recorded video each and the live discussion afterwards because, well, the time zone is rather unfortunate. So we're speaking with Europe, I suppose, in both cases. And first talk is from Konrad. Hey, Konrad, you're there?
Yes, I am there.
And we will now play your video, and afterwards I will introduce the discussion, right? Okay, so let's...
Okay.
It's a little bit blurry, but I think we
Good morning, everyone in Pasadena. I'm sorry that I cannot be there with you today, but I hope that we can still have an interesting discussion after my pre-recorded talk. I will now give an overview of my Onward essay, Redressing the Balance, a Yin-Yang Perspective on Information Technology. But before doing so, I'll say in a few words where I'm coming from. Unlike most of you, I am not a computer scientist. I'm a computational scientist. I studied physics, and then I did research in computational physics, chemistry, and biology for a bit more than 30 years. It started with my PhD in 1990, where I worked on colloids, which are simple systems. I did prototyping using APL on an Atari ST, and then I wrote production code in Fortran 77, which I deployed on IBM mainframes and YMP supercomputers. That was a rather satisfying setup for the time. Then in 1994, I moved on to studying proteins, which are complex systems. And there I discovered a universe where everybody ran Fortran spaghetti code that nobody understood anymore. And I also had my first contact with irreducible computations. That is, the same program gave different results on two different machines, which from my perspective were identical. These experiences led me in 1995 to become a co-founder of Numerical Python and then the scientific Python ecosystem. But in 2010, frustration with Python set in as well. So I could give as an alternative title of this talk, 30 years of dissatisfaction with scientific computing. The yin-yang lens that I will apply in my analysis is unfortunately not easy to describe in a few minutes. It's its origins in Chinese philosophy, where it is seen as a duality that is fundamental to the universe and expresses itself everywhere. I'm borrowing it as a tool, as a lens to look at things, and in particular to look at processes which have opposing characteristics but are also complementary and feed each other. The image behind these terms is a mountain illuminated by the sun. It has a shady yin side, which is dark and absorbing, and then a sunny yang side, which is bright and radiating outwards. In the course of the day, the sun moves around, and it is different parts of the mountains which are yin and yang. So this is a dynamic rather than a static picture. As a simple application of the yin-yang lens, consider a conversation between two people. Listening is the absorbing phase of the conversation. It is the yin phase, whereas speaking is the radiating outward-going phase, the yang phase. The yin-yang lens is typically used to watch out for harmony or balance. And this is a nice illustration because a conversation in which one person always speaks and the other one always listens is not balanced. Balance requires a back and forth on both parts. I will use the yin-yang lens to look at how people interact with the world around them, where people could be individuals, but also teams or even society as a whole. And the world around them includes both the natural environment and other people. Yin phases in this context consist of absorbing information from the outside world and adapting your inner state to it. This means activities such as observing, learning, understanding, and trusting. Whereas yang phases consist of reaching out and changing the world, using activities such as manipulating, constructing, or shaping. A nice example of a yin-yang pair here is science, the yin phase, engineering, the yang phase, both looking at how society as a whole interacts with the natural environment. Up to here, it looks like yin and yang are symmetrical, but there's also the widespread notion in Chinese philosophy, in particular Taoism, that yin is a kind of preparation for the subsequent yang phase. Taoism has the central notion of wu wei, which is often translated as effortless action. The idea is that you should respect the order and flow of nature and perturb it as little as possible. That means when you do something, you first need to understand the situation, know about your options, and then act by minimal intervention. So this is clearly yin, yin, yin before yang. Contrast this with the Silicon Valley philosophy of move quickly and break things, which is yang, yang, yang. Well beyond Silicon Valley, today's Western societies have a very strong yang focus. We talk about economic growth. Engineers are looking for solutions that scale. All these are yang terms, which I show here in blue in italic script. Another example is that the notion of progress, which was quite prevalent when I was a student, has largely been replaced by the term of innovation. Progress is a bit like Wu Wei in Taoism. It requires to know what is bad about the current state so that you can improve it, whereas innovation is just, let's do something different. But perhaps the most striking illustration for this phenomenon is that science, the quintessential yin activity, has been invaded by a yang vocabulary from industry. We talk about knowledge production, we have research outputs that are supposed to have impact, and we have research management. The question I want to discuss in the following is, what can we do to strengthen our yin processes? There are basically three computational techniques that support the yin processes of learning and understanding. The first one is computational modeling, in which the models we form during learning are encoded as formal systems. This means that we can manipulate them with a computer and thus test our understanding of the natural world. This requires supportive modeling environments. And I think in the 1990s, APL was such a supportive modeling environment for me when I was studying colloids. Whereas today, I have still not found a supportive modeling environment that is good enough for studying proteins. The second technique is simulation. In simulation, we have a ready-made model, and we simulate it, and then we learn from the results. Learning from the results means that you know how to interpret them, and that requires a good mental model of simulation code, which is often difficult to achieve. The third technique is data analysis, which means interpreting observations in terms of trusted computational models. And much as for simulation, this requires a certain trust in the code. You have to trust the code to implement the computational models faithfully. I will now look at some of the tools and techniques we use to implement these basic computational methods. I will point out their yang focus and suggest more yin-friendly alternatives. I will start with environments for computational modeling. These tools are for building executable models and thus implement a yin phase that prepares a subsequent yang phase. Programming languages are very yang focused. They are made for constructing programs in view of execution. Change and adaptation, that is, adapting to new observations or changing hypotheses, happens outside the language. You use an editor to change your program and then you compile and run it again. This makes for large and slow yin-yang cycles. Live programming environments such as Lisp, Smalltalk or APL are made for supporting an alternation between adaptation and execution. This makes for small yin-yang cycles that gives rapid feedback, and rapid feedback supports learning. But we could go even beyond that, because we have a much more yin-friendly technique, which is specification languages. Specification languages actually made for modeling rather than executing. You don't have to have a complete specification. You can write down pieces of it as they come. You can combine them freely, and you can explore them using tools such as model checkers. Unfortunately, specification languages are used today mostly in formal methods for validating large software systems. That is again the yang process of constructing software systems. We do not have interactive modeling environments that use specification languages. The type systems we have in programming languages are also very yang focused. I would even call them totalitarian. There is the one and only type system of your language, and everybody has exactly one type. In a more yin-friendly world, we would have partially and focused type systems. We would make our own type systems as part of computational modeling, decide to which values they apply, and combine multiple type systems as needed. Here's how this works in physics, which has used type systems since the 19th century. Here's an equation from classical mechanics It says that angular momentum equals moment of inertia times angular velocity. Now we can apply one type system to this that comes from tensor algebra. This type system says that I, the moment of inertia, is a tensor of rank 2, whereas omega, the angular velocity, is a vector, meaning a tensor of rank 1. Then it follows that the contraction of the two, I times omega, necessarily has rank 1, and thus L, the angular momentum, must also have rank 1. Independently, we can apply another type system, which is called dimensional analysis. Here, we see that the moment of inertia, I, has dimensions mass times length squared, whereas the angular velocity, omega, has dimension 1 over time. The product must then have dimension mass times length squared over time, and that means that L, the angular momentum, must also have dimension mass times length squared over time. These two type systems are independent and can both be applied to the same equations independently. Next, I will look at tools and techniques for implementing simulation and data analysis. These are about deriving insight from computation. They are about yin processes that happen after the yang process of computation. The most important tools here are programs, simulation programs or data analysis programs. Programs are yang artifacts. They are made for execution, and we judge them according to criteria such as the efficiency of execution or how good the user interface to execution is. For the yin phase of interpreting, understanding and trusting the results, something else is much more important. That is that users can have an accurate mental model of them. And not only an accurate one, but also a complete one. There should be no hidden functionality. Hidden functionality may suggest things such as smartphones secretly spying on you, and that would actually be a good example. In computational science, we have more mundane and less malicious cases. As an example, a former office neighbor of mine had to throw away the results of 3 months of supercomputer simulations after discovering, by accidentally reading a footnote in the program's documentation, that there was some optimization step implemented, switched on by default, for making nicer visualization videos out of the data. And these steps completely ruined the data for his purposes, which were different from what the program's authors had initially in mind. So for me, something that is documented in a footnote qualifies as hidden. There is another aspect to this, which is that mental models that users form are invalidated by rapid change. Nowadays, programs tend to be updated very frequently, and you cannot really develop trust into a piece of software that changes faster than you can understand it. In philosophy of science, such issues are grouped under the label of epistemic capacity, which is philosophers' jargon for you don't really know what is going on inside a computer. When computers started to become widely used tools in science in the 1980s, this was a topic of debate among early practitioners. Some raising doubts about using a tool for research that you can't really understand deeply. Others saying, well, as long as you write your own code, that's okay. And yet others saying, these simulation programs are so great and offer such great new opportunities, we have to use them and then we'll figure out later how to deal with the uncertainties about the meaning. Sherry Turkle has written a nice summary of these discussions, these debates, in her book Simulation and its Discontents. And she summarizes them as a tension between doing and doubting, which fits my analysis very nicely because doing is yang and doubting is yin. As we know now, doing has won, and the uncritical use of computer simulation has become widespread in many scientific domains, including my own. But the problem is still among us, and today we discuss it in the context of AI. The search for explainable AI is not very different from the search for fighting against epistemic capacity. We actually never tried so far fighting epistemic capacity for good old algorithmic simulations. And that is exactly what I propose in the following. An old idea in this space is the idea of readable code. Here's a quote that you've certainly seen and maybe even cited yourself. Programs must be written for people to read and only incidentally for machines to execute. It's from the textbook Structure and Interpretation of Computer Programs by Abelson and Sussman. And I think they're actually doing a pretty good job in their book, writing code that is written for people to read, but those people are future programmers, and the code is textbook examples and not real-life code. In the context of computational science, the question is, can we write code for users to read, such that users can form a good mental model of the code? And let's immediately change this question slightly, because reading is only one mode of interacting with the program. I would rather say for users to explore in view of reaching a good understanding. Here's an idea I would like to propose for doing this. I have not tested it, it has not been tested by anyone else, but I think it is worth testing. The idea is to provide code as progressive explanations in multiple layers. The first layer a user would face is the documentation layer. It would explain in plain English what the program is supposed to do and how it goes about doing it. But then we could embed formal specifications in this layer and also executable examples. And these would allow the user to form a more precise mental model and to verify that it is actually accurate. A second layer would be a high-level implementation. It would contain all the details to be fully executable, but it would not include any optimizations, neither for speed, neither for memory or other resource use, nor for adaptation to a specific type of hardware, just the basic algorithms. And then in a third layer, an optimized implementation, which is what people would actually run, executable by a machine. The obvious challenge is to keep these layers coherent as they evolve. This is certainly not easy, it doesn't sound impossible either, and I think it is worth trying. As an illustration how such progressive explanation could work, let me show you a prototype I've been working on that implements some of these ideas. What you see here is Glamorous Toolkit, a modern Smalltalk environment. It contains a knowledge-based system which implements something like a personal wiki. And what I've added to this wiki is the possibility to embed formal specifications in the text. Everything you see in blue on the left-hand side here is part of a formal specification. Here, for example, you see a differential equation, which, well, this is a parse tree, but it is an object in memory that you can explore and do computations with and exploit in various ways. For example, you will see a bit further down a piece of simulation code. This runs a simulation based on this differential equation. And then you get a time series as a result, and you can get a plot for that. Okay, so now let's suppose that we have found a way to make code readable for users. It is still not reasonable for a user to read all of the code that they use for some project. There's simply too much of it. So there is still a need for users to trust software at some point. Developing trust is another yin process, and it's a yin process that is badly supported by today's software architecture. So what kind of mechanisms do we have for developing trust in software, and how would software have to be structured in order to make such trust development possible? I will start with a category that is particularly important in scientific computing, that is domain software. That is software that embeds scientific knowledge of a specific domain and is used to solve domain-specific problems. So this would be a climate model, this would be a protein simulation engine, or etc., etc. If you ask computational scientists what software they use, then all the names you would get in reply are names of domain-specific software. So here, the main source of trust would be openness to inspection. Because even if you don't read the code yourself, the mere fact that it is readable, and that is both legally readable and practically readable, means that you and your colleagues can check it if you want to. And that by itself is a source of trust. The other source of trust, and today the only one because our code is not readable, is trust by reputation. It is say, okay, I trust this piece of software because all of my colleagues use it, they have good experience with it, and they're happy with it, etc., etc. But here, the big risk is a trust bubble. That is, everybody trusts the software because everybody else seems to trust the software, and this trust is not grounded. There's nobody who has actually critically examined it because it is not examinable in practice. And I think this is the case for many of today's scientific software packages. The second category I see is what I call infrastructure software. Things like compilers, data management tools, foundational algorithms such as linear algebra from my domain. This is software that people typically use and even depend on without being aware of it. It is used indirectly, it's dependencies of the domain software. And a nice way to develop trust here would be to treat them just like any other industrial product, like a fridge, like a car, like a television set. That is, we trust these devices because they are widely used, they are examined by others, and these people write about them. This would be reviews, this could be journalists or whatever. There could also be audits, official audits, there could be norms, regulations, certifications, etc. If I trust the brakes of my car, that is because I know that there are security rules behind it that are enforced by state control entities. And there's also, of course, still trust by reputation that would in this case be something like brand names. The third category is what I call situated software. It's scripts, notebook, makefiles, short pieces of code that are specific to a research project and that you would mostly read to learn what has been done or read as a source of inspiration, and then you would write your own code and use those ideas, but you would not reuse the code identically. So the object of trust is already a bit different. Such software is always built on top of infrastructure and domain software. And trust here would come from reading, of course, but also from personal relations. If you're in a team, for example, you're working on a research project in the team, and there's one person writing the code, then the other people would typically trust this person because, well, that's our computer person, and well, that's the kind of relation you have. And the same could happen in a family or in a work team and other situations. In those three boxes, I have indicated a numerical metric that you can use to judge in which category a certain piece of software is, and it's based on the number of contributors, NC, and the number of users, NU. So for situated software, there's typically one contributor and maybe 10 users. I'm limiting myself to orders of magnitude here. It's only powers of 10. Domain software would be characterized by a ratio of user to contributor numbers, which is something between 10 and 1,000. And infrastructure software would be, this ratio would be above 1,000, so many, many more users than contributors. The main obstacle to trust development for domain software is that the code is not readable for users. Code is readable only for developers. And in practice, for these small communities, anybody who has both the technical and the domain competence to read the code is probably part of the development team, so there is no independent evaluation. For infrastructure software, the external evaluation would have to be done by paid professionals, supervised by institutions. But today we do not have such institutions, nor do we have the legal frameworks to make this happen. So in practice, today, both domain software and infrastructure software can only be trusted through reputation, and as I already pointed out, this often leads to bubbles. So that's what I wanted to tell you as a first overview. In conclusion, my main thesis is that our world is increasingly young-focused, and that as a consequence, yin computing has been neglected for decades. However, there are interesting challenges for research and development in this field. A few topics I've told you about are interactive modeling environments for specifications, yin-friendly type systems, user-readable code, and trustworthy software. I am not an expert on the computer science aspects of these problems, but I would love to collaborate on such topics with people who are, so if you are interested, please contact me. And of course, there is more on the essay, so please read it. Thank you for your attention, and I'm looking forward to your comments and your questions.
Yes, so thank you again for your video, for your talk. And so, do we have a first question? I think there are a lot of aspects in this talk. I liked how you summarized what a Smalltalk system is in this yin-yang perspective. And I never imagined to expand the simple, oh, it's a quick feedback loop, to this theory. So it's really interesting to think about light and dark and these opposites. And now I'm thinking about the simplicity talk, but just maybe because of the light of all the contrasts that had. So we have a question from Mary Shaw. Go ahead.
Thank you for a thoughtful and provocative talk. I'll ask a question about a particular detail, which is the documentation.
Can you go?
Oh,
it's still.
Is the micro?
No, it's.
Is there an on switch?
Are we still figuring out the other microphone? No, that's something. Yeah, approach is a little bit more. Okay. Go ahead.
Now I'm in. Thank you for a provocative talk. I'll focus on a question on a particular aspect, which is the documentation layer. My observation over the years has been that the things that get kept up to date are the things that have to be accurate or the build breaks. And usually that's the code. When we were working on architectures, we tried to build a system in which it was the high-level description. And so in that vein, my question is whether you can imagine some form of documentation that is user-readable, perhaps not free-form text, but more structured text, that is at least checkable as you compile the code, so that discrepancies between the documentation and the code break the build and you force updates. Do you see a prospect there?
Oh, wait, we need to. Can you unmute your microphone? You're muted. Sorry, can I hear you?
All of us get to be muted.
Yeah, now we are.
Yeah. Okay, yeah, sorry, I didn't. Okay, yes, I mean, this is exactly my idea of embedding formal specifications in the documentation. And this is actually the first step I've done in a prototype. So the idea is, that in the ideal world, we would have formal methods to check equivalence, or at least tests. It doesn't really matter which technique, but there would be some technique of ensuring that what is embedded in the documentation actually corresponds to what the code really does, yes.
Thanks for the talk. I had a flashback moment to literate programming, which didn't really take off. That was done in a Smalltalk environment, but the idea was to explain your program and then have it there. And then the other thought that crosses my mind is the notion of well-constructed Jupyter notebooks, sort of where I can execute some code, but there's still this responsibility in any of those approaches for someone to care about and curate the entire process that the entire environment that you're talking about. And I think that it would be, remiss to say, well, we can just do the Yang solution of write unit tests for all of it, and there it goes, we're done. I think it's a curation process that someone has to care and curate that. And so I'd want to know your thoughts on that as well.
Yeah, I fully agree. In fact, I mean, the Jupyter notebooks and others, the idea is derived from literate programming, right? So literate programming goes back to Donald Knuth at a time where, well, computers were very different. And the problem with, I mean, in my domain, notebooks are used very, very much. And the problem is they are really in the layer of situated software, as shown in the end. This is really a very small part of the whole software stack that you can actually document in the form of a notebook. And what you're actually looking at is a linear sequence of code blocks,
right,
nicely documented with results. But in reality, they just call stuff from a library, and you cannot see them or test them or whatsoever. So
yes.
It's really just the tip of the iceberg. And that's why I don't think it is sufficient. Yeah, this is why actually the system I've shown, my small prototype there, is built on a Smalltalk system which has such notebooks. So I can do actually the short simulation of the Lotka-Volterra equations I ran. That's exactly that. That's a piece of Smalltalk code that is embedded into such a notebook. The difference is that in my case, a part of the notebook is formalized, and the simulation actually picks the equations it solves out of the text. so they are guaranteed to be the right ones.
So that's
And
matching.
that gives
Yeah.
you more.
Yeah.
Yeah. So you're sure to, let's say, what you read is what you run, in a sense, and you can. So you can, as a user, you can edit your equations, you can change a prefactor, and it will automatically be taken into account in the simulation. So it's the coherence is much stronger, and you have a much larger part of the whole code which is visible in front of your eyes and which you can edit.
So I have one more observation thing to share with you. There's this book of patterns by Cyril Martrere that's called Living Documentation. And it was written for people who want to not have things get out of sync, but to have, from a software engineering point of view, have patterns in place and hooks that you can do in order to keep any sort of thing that you might generate in sync with the actual code. And there might be some useful patterns in there for you to think about. I think it's a great book.
Thank you. I've never heard of that book. I'll look at it. Thank you.
Hi, Conrad. It's it's Lou here. Thank you for that talk. That was
Okay. Yeah, I can't see you, but I recognize your voice. So, yeah.
okay. Great. Hello. Yeah. Thank you. That was really thought-provoking. It's making me think about some of the projects that I work on now in a new light. One thing I wanted to ask was, why do you think we are so biased towards this yang perspective? You know, is it something to do with the human condition or the world we live in? What do you think is the reason for that?
Yeah, it clearly goes well beyond technology, computing science, and all that. On the contrary, I think we are kind of inheriting this from our outside world. I mean, there's an easy explanation. Say, oh yeah, this is just capitalism, growth, whatever. Actually, if you look at the Taoist philosophy literature, they have complained about yang dominance, 2,000, 3,000 years ago. So it's not really a new phenomenon, and I don't know. I mean, this is just descriptive. It's not an explanation, of course. So yeah, I think it's probably part of human nature. Yeah, and I think the Taoist philosophy was that you have to act against it. It's not good. You have to act against it, and that's kind of what I'm trying to do as well, in a way. Yeah.
Great, thank you. That's an interesting extra piece of information. Thank you.
Hi. So I kind of have the feeling that software development has been getting much more yangy in recent years, and that some of the popular development processes, the agile movement, continuous integration, continuous shipping have pushed more and more emphasis onto the code and coding as the sole important artifact. And if I think back to really ancient times, and certainly I started quite young, but in the era where you had to punch things in the cards and you had hour-long, if not day-long turnarounds, you thought a lot more before you committed to the key punch, and people stretched things out on paper, wrote little diagrams, and then translated that in the code. And my sense is that those pre-coding steps are more yin.
Yes, of course.
I think. I'm wondering how we can push things back so there's a little bit less immediate code emphasis and more emphasis on the yin side.
Yeah, well, that is exactly what I'm trying to do, and of course, I'm not saying that we should get back to making things expensive, making mistakes expensive, and this was the reason why you had to think about things before, right? Not saying we should necessarily get back to that, but I would say we should, I said, that was my idea of we should have better feedback loops and discover problems early. And for me, this means that what we should actually have a modeling phase. You would probably call it differently in software engineering, with requirements or whatever. In science, I would call it a modeling phase. And I think the important part for me is that this is not the same. This is not a form of programming, right? I mean, there's explorative programming. There's kind of overlap, but I think it's the same activity looked at from two different ends. So computational modeling is the goal, and explorative programming is the technique. And I think we need to emphasize the goal more than the technique, and say, okay, maybe programming tools are not what we need. We probably need modeling tools, which necessarily implies some form of programming, but they are different tools made with different priorities for ultimately a different task. And yeah, and that task would be making you think, making you look at preliminary results and refining your model before you actually run big things.
Yeah, and I'm certainly not suggesting we go back to punch cards and flowcharts. As a matter of fact, at my core, I'm a Smalltalk programmer, and that's the most impactful thing on me, which is a very, fast turnaround cycle. But the thing, as I think about my experience as a Smalltalk programmer, I'm not thinking about coding, I'm thinking about modeling. And that the end result is a model that happens to execute rather than a pile of code. As a matter of fact, one of the...
if you read the original papers, if you read the old, I read many of the old papers by Alan Kay. I mean, this is the idea. I mean, that was even for children, right? Mm-hmm. The Diner book idea. And so, yeah, this goes very much in that direction. And I mean, it's also, I also ended up working with Smalltalk. Actually, I almost have the impression of being at a Smalltalk conference there. I've never seen so many Smalltalkers outside of a Smalltalk conference like here.
Well.
Yeah, I fully agree.
OOPSLA, which, SPLASH is the umbrella that we're here, was started by Smalltalkers for Smalltalkers.
Okay.
So thank you.
There's time for one more question.
Hi, Conrad. Thanks for a really interesting talk. I found the lens of yin and yang to be a fascinating one that I'd not seen applied to software before. And it also reminded me of a book that I haven't read, but was summarized to me. And the book is by Ian McGilchrist. It's called The Master and His Emissary. As I understand it, the thesis is that society is becoming increasingly more left-brained. And the sort of the right-brained nature aspect of our nature is sort of deprioritized. And I wondered is that known as a thing that kind of overlaps with yin and yang? Has there been some sort of alignment of those, or maybe they're actually separate? I don't know if that's something you've seen or thought about before.
I've certainly not read anything about it, but my first impression is that they are neither identical nor completely unrelated. So there's some overlap, but it's not quite the same. Not quite the same criteria which is used to. So, I think you can use both yin and yang phases and left-brained and right-brained in principle. But unlike you, I've heard about that book. I haven't read it. So there's something in common there. So.
We'll must read and compare notes later. Thank you.
So Let me look at the time. Well, I will use the last minute. I have a question about readable code and optimized code. Well, how many levels do you think we need, thinking of high-performant virtual machines? So we have this separation of two layers, basically, right? Take a Smalltalk VM. You have can write readable Smalltalk code, and the VM takes care of optimizing things. But I'm thinking of that's not what you meant when you have maybe these different. Are there more than two layers of these things?
No, I think from the users, from the documentation point of view, I really want two layers, and I've added the third one, saying, okay, well, maybe we need another one for technical reasons. But if you can get rid of, if you can get sufficiently good code generated from the second layer, I think sometimes. See, I said this for me, the second layer has all the details, but it might even be algorithmically inefficient. So, and I'm not sure that optimization techniques, automatic optimization techniques, would be able to substitute an equivalent, more efficient algorithm, for example? Well, why not? I mean, maybe some pattern detection. Ultimately, there are not so many algorithms of this kind, so maybe some plain pattern detection could do it. I don't know. Maybe worth looking at, but.
Thank you. Let's thank the speaker again. And our next talk is also pre-recorded. And I checked, I think Al and Robert are here for the live Q&A afterwards. And the talk is called Programming Languages for the Future of Design Computation. So let's stream.
Programming languages for the future of design computation. Design computation is the embedding of computation within architecture, engineering, and construction practice. The application of existing design computation languages has already had a major influence on architecture and construction. To give one example out of the thousands of buildings already developed with design computation, this is the Louvre in Abu Dhabi, the Dome of the Louvre in Abu Dhabi. The construction is a complex lattice roof which creates a local microclimate in the space below, creating a rain of light. The size, complexity, and digital fabrication of this project could only have been achieved through highly computational and automated methodologies. The full paper describes the context for design computation, but in this short presentation, we want to focus on the key language insights. This essay addresses the question, how can innovation in programming languages support innovation in architecture and engineering? However, our starting point is to review the use of existing design computation systems. This reveals a number of important issues of representation, for example, of architectural data and logic, and usability, for example, from an end-user programming and pedagogic perspective. We suggest that addressing these issues provides some interesting opportunities for program language research. So while design computation can be defined as embedding of computation within architecture, we need to distinguish design computation from the use of standard geometric modeling applications which are used to support conventional architectural design. In these conventional applications, modeling is by interactive graphical editing using direct manipulation, leading to 3D geometry models, the generation of conventional 2D drawings, and a manual mechanical construction process with no programming skills required. The resulting architectural designs are represented as static data models. These models represent the outcome of the architect's design thinking, but the underlying design rationale is not recorded. This can be compared with design computation. This is based on end-user programming to generate a solution space of design options, leading to the direct digital fabrication and potentially to robotic assembly. The idea that to explore alternative design options, it's really easier to change the design rules and logic in the form of a compact and explicit and re-executable design computation program than to manually edit the gigabytes of geometry model in the generated output data. And when we say easier, this is not just a question of time and productivity, but the sense of agency and creative empowerment which computation gives to architects and engineers. But initially, due to the lack of appropriate end-user programming languages, design computation was only accessible to a few architects and engineers who were also accomplished professional programmers in such languages as C++, as illustrated in the example shown, which is the design of the roof of the Great Court of the British Museum. The need to learn a professional level language became a barrier to the more widespread adoption of design computation. Hence our interest to create languages which are more accessible to the wider community of architects and engineers. Therefore, design computation, we can describe design computation as a form of end-user programming, where a professional architect or engineer with major project responsibilities, but with little prior programming experience, learns to program and thereby to more effectively solve domain-specific problems. Effectively, design computation combines an educational progression for the professional end user from entry-level skills to proficient programmer, an architectural progression from the design of an initial exploratory architectural concept to the detailed construction specification, and a corresponding software progression from an initial exploratory program to more precise and structured software engineering. The challenge is to create languages and programming tools which are more accessible to entry-level users and which initially can be used without conventional programming skills, but which are still sufficiently empowering so that users can create more inventive, appropriate, and performative architecture which can go beyond many of the limitations associated with some of the conventional architectural design applications. A number of visual programming systems have been developed and adopted within the design computation community and taught within many university schools of architecture. And these have been instrumental in the design and fabrication of many significant buildings. Most of the visual languages used in design computation are based on directed acyclic graphs or DAGs, and therefore do not directly support any iterative programming. Apart from this constraint, the intent of these existing visual languages is to lower the abstraction barriers to programming by the simple expedient that these visual languages present hardly any established computing abstractions. First, visual languages typically only present a limited subset of the features found in more complete programming languages. Second, there is no need for the user to learn text-based syntax. Third, variables can be unnamed. References are realized by the graph arcs between the nodes of the visual program. Fourth, there is an implied form of typing, but here the direct manipulation program editing tools guide the user so that the output of a particular type can only be used as input to a compatible type. Fifth, operations are typically overloaded for collections so that the user does not have to learn about or explicitly program iterations. And sixth, and possibly the most contentious, visual languages provide an easily used editing tools such as copy and paste. As this example demonstrates, many of the available visual programming languages are very attractive and easily learned, and the apparent freedoms offered by these languages and programming tools makes it really easy for entry-level programmers to create perfectly executable visual programs. The apparent simplicity, lack of abstractions, lack of constraints, lack of syntax, and the ease of use of visual languages create what we might term a mirage of convenience in which the inexperienced entry-level users are drawn into a form of programming using very simple constructs, but on an unconstrained scale, where the cumulative visual complexity can make the resulting programs incomprehensible and in some cases uneditable. The danger is that users unknowingly drift into a completely unsustainable form of programming. Of course, all programming languages can be misused, but what we find most troubling is that it is the intended use of visual languages by entry-level users which can so easily lead to this unsustainable form of programming. We have come to the rather unfortunate conclusion, to quote George Orwell, that the slovenliness of our language makes it easier for us to have foolish thoughts. Therefore, as a constructive response to these representational and usability issues, we propose a system of 4 languages built around established conventions of visual and text-based programming. These are, first, an initial language, most probably a visual language. The challenge is how to harness the recognized advantages of visual languages, but to limit this role so as not to allow the unsustainability experienced with the extended use of existing visual languages. Second, a transitional language to provide the end user with a learning pathway from the limited entry-level visual languages to programming proficiency with text-based languages. This then leads on to the third language, a target language. Typically, these are industry standard general purpose languages such as C# or Python. And fourth, an extension language, which addresses the particular domain-specific requirements found in design computation and allows the users to go beyond the functionality available in the conventional general purpose languages. So the four-language system we are proposing recognizes the pivotal role of established languages. The initial and visual and the transitional languages are intended to provide an on-ramp for the entry-level programmer to become proficient with the target industry standard languages. And the extension languages enables the now proficient end user to harness more advanced computing concepts and programming language innovations. Now we will consider the four languages in more detail. And here we are using a minimum example, creating a 2x2 array of points to illustrate the issues of representation and usability. First, the initial language. This is a typically a simplified visual programming language which addresses the needs of the entry-level end user. The key features of this language are data flow programming, implied typing, and with operations overloaded for collections. Rather than offer yet another visual language, we propose to consider the more strategic issues by suggesting the key tenets which might be applied in the design of a future visual language, and in particular to respond to the recognized limitations of existing visual languages. First, we need very careful agreement on the key programming concepts which might be included in such an initial programming language and whether these are really suitable to be presented in a visual form. If it is a visual language, then the system should include a mechanism to warn the user when the visual program is approaching the limits of legibility. Third, the visual language should be easily transformable into text-based code using appropriate conversion tools. And fourth, the visual language should avoid using any non-standard functionality or terminology which will not be available in the subsequent transitional or industry standard languages. We want to avoid, during the user's migration from visual to text-based languages, that the user has to unlearn skills and terminology which have only just been acquired, which were now no longer relevant in the subsequent languages. In short, an initial language should lower the barrier to adoption. But a common limitation of visual languages is that of the accumulative visual complexity. The larger the program, the less comprehensible it becomes. Therefore, it's also important that the visual languages should also lower the barrier to migration to more capable text-based languages, and hence the concept of a transitional language. But it's also important to identify the critical inflection point between the visual and the transitional language, where the program has served its purpose to attract the user to the idea of programming, and where the initial program has offered the user sufficient benefits to reward their investment to learn to program, but where the user begins to understand that visual programming offers diminishing returns, and where the user is open to other programming opportunities rather than continue to expand the visual program, for example, with cut and paste methods. Second, the transitional language. This introduces the user to simplified text-based notation and gives the user access to regular programming concepts and functionality while deferring some traditional programming challenges. The key feature of the transitional language is a automatic node-to-code conversion based on a one-to-one mapping between individual nodes in the visual language and corresponding individual text-based program statements. Programming tools, also other additional programming tools for code expansion, so that the concise program statements which exploit the built-in overloading for operations for collections in the transitional language, can be expanded to become iterative structures compatible with the target language. The features we propose for the future transitional language have been developed from ideas originally explored as part of the design script language. The advantage of the one-to-one mapping between visual nodes and text-based program statements is that it allows the entry-level programmer to learn text-based syntax by observing the correspondence between the visual, transitional, and target languages. In exploring the progression of languages, this has made us acutely aware of the usability issues involved in designing languages for entry-level end-user programming, issues of visual complexity versus succinctness, and how the users are expected or encouraged to structure their programs, shallow and wide versus narrow and deep. One of the key objectives of the design of the transitional language is that the user should gradually be introduced to concepts such as collections, flow control, functions, typing, and classes, which are essential to help the entry-level programmer to move away from the rather unstructured, data-centric emphasis found in visual programming and to express their application ideas in more appropriately named, typed, and structured schema and classes. The key role of the transitional language is to ensure that any modularization and schema definition methods supported by the initial visual language are directly translatable into types and class definitions found in the target languages. As the name suggests, the transitional language integrates two program paradigms: data flow to be compatible with the preceding initial visual language, and imperative to be compatible with the succeeding industry standard languages such as C# and Python. The features and programming tools of the transitional language are intended to nudge, that is, to subtly encourage a change of behavior in the entry-level programmer by first altering the attractiveness of an early move from visual to text-based programming, and second, altering the attractiveness of modularization compared to copy and paste. This combination of programming paradigms also allows the transitional language to support interesting forms of hybrid visual text-based programming. This presents the opportunity for the visual layout and the connection of the nodes to be an analog of the layout of components within a physical system, while the code within the nodes can define the behavior of the components. This illustration of hybrid visual textual programming is a retrospective functional model of the MIPS microprocessor. Fourth, the extension language allows the more direct expression of concepts found in design computation and also to improve the correctness of end-user programming beyond the functionality of conventional languages. But before we introduce the extension language, we would like to give you some insight into the context for design computation. Architecture and building engineering consists of a number of individual specialisms. In fact, it's a form of multidisciplinary collaboration. However, the reality of a building is that it is a complex system of components, for example, structure, facade, services, where the different physical properties of a single material component, for example, a wall, may contribute to the performance of multiple engineering systems. So considering such a wall example, the physics and performance criteria of a single component may cross many discipline boundaries. We might consider such a physical component as a tangible embodiment of this multidisciplinary collaboration. Delving a little deeper, we might be aware that many of the key innovations to create more performative buildings are likely to come by harnessing such multifunctional components in a process called building systems integration. In this context, it's not sufficient for each discipline to optimize the performance of the separate engineering systems in isolation. On the other hand, in both programming and architectural design, it is generally accepted that problem decomposition down to clearly defined functional units is beneficial. But how can this approach be adapted to suit the level of problem complexity suggested by building systems integration? What is interesting is that at a collaborative team level, the process of building systems integration is effectively a form of constructive negotiation between different engineering specialists, where each is attempting to maximize the contribution to the overall performance of the building without constraining the ability of their colleagues to do likewise. Our intention is to design the extension languages so as to address the challenges of representing and reasoning about complex systems composed of multifunctional components in order to aid the type of interdisciplinary negotiation required to create more performative architecture and to realize new forms of building systems integration. There are three key features of the extension language: units of measure, interval computing to support variability, tolerances, and uncertainty, and connected connections. So first, units of measure. Most programming languages only provide a limited set of numeric types, for example, integers and floating points, to represent completely different physical quantities, for example, length, force, and angle. This lack of dimensional information can lead to undetected numerical errors arising from inconsistent dimensions or units of measurement. For decades, it has been recognized that dimensions and unit information can be seen as an extension of standard type systems. Units of measurement typing, for example, developed by Kennedy, instead embed the rules of dimensional analysis into the programming languages. Typically, this would be based on the SI units as illustrated in this slide. Going further, variables could be qualified by a hierarchy of attributes: dimensions, for example, length; units of measure, for example, meter; and kind of quantity, for example, thickness. These attributes can then be enforced automatically by the compiler. Some attributes can be inferred from use, and conversions can be automatically derived. The implementing of units of measure types in a future design computation language would provide important advantages to the users by improving the human readable programming semantics, while a fully units consistent program, being machine readable, can be verified as free from any dimensional errors. It is anticipated that some aspects of units of measure types can be retrofitted to industry standard languages, for example, using C# attributes. The second extension language feature is interval computing, which is intended to support variability, tolerances, and uncertainty. Now, we've already talked about the multiple contributions which a single building component can make to the overall performance of a building. But in addition, the initial conceptual phase in the building design, there are often a complex process of optioneering, trade-offs, and negotiation between different design and engineering disciplines, where the use of an acceptable range of values, for example, for dimensions, tolerances, and performance measures, is potentially more realistic and therefore more useful than the use of a single over-precise value. In this context, the use of precise values might be confused with certainty. Yet existing digital modeling tools typically only support nominal absolute values, such as dimensions, with tolerances only specified as annotations. This severely limits the designer's ability to reason about the critical role of uncertainty, variability, and tolerances. Returning to the example used to define the schema, create a new class definition. Applying units of measure and interval types to this example, it could be transformed into the following slide. Overall, with existing languages, a numeric value can only be defined with a less precise type and an over-precise value. we see the potential to combine units of measure and interval computing within a future design computation language. This would radically improve program semantics and allow the user to directly express the specificity of a variable's type and the option to explicitly recognize its uncertain value. The third extension language, these are the two examples. The third language extension is complex collections. As previously discussed, it is recognized that buildings are composed of complexly connected collections of physical components and enclose equally complexly connected collections of spaces. While these collections are often hierarchical and can be defined top-down, many of the important queries which allow the user to reason about these relationships often need to operate bottom-up. Staying with our wall example, we might consider a top-down system of collections where the building is composed of rooms represented by topological cells, which in turn are composed of walls represented by topological faces. But a reasonable bottom-up query might ask which walls are shared by and therefore connect which rooms. In standard object-oriented practice, one object can point to another via a field or property denoting some relationships. However, with conventional languages, this relationship is not invertible, i.e., knowing which object points back to an object requires manual accounting. In fact, many proprietary applications used within design computation, for example for structural analysis, energy simulation, digital fabrication, etc., already implement equivalent functionality, but in a proprietary and opaque way. Therefore, the end user programmer may be aware that this functionality exists, but it's just not available for more general application and reuse within their programs. Instead, adding connected collections to a future design computation language will ensure that the inverse mappings from the constituents back to the collection is automatically maintained. This allows designers to directly and conveniently build and query many different types of connectivity, such as complex assemblies, engineering systems, circulation, and egress routes. A prototype of connected collections has recently been completed and tested with the examples used in this paper. Addressing the overall extension languages, as with other languages in our system, we outline a number of key tenets for the design of a future extension languages. The extension languages should leverage existing type checking support and syntax. It should use type inference but allow compilers to automatically insert inferred types into the code to aid documentation and user understanding. New syntax should be introduced very sparingly and only when required to express new functionality which cannot be emulated by the use of established functionality and familiar syntax. It should enable end users extensions of domain concepts to use projects and engineering subdisciplines, and features of the extension language should be backwardly compatible with other language layers in the system. It should allow progressive formalization as a style of optional typing so that type information can be added gradually. For example, it should enable static types to be initially created dynamically. Overall, future design computation is likely to be a conversation between human reasoning and machine intelligence, with each posing problems and explaining methods and solutions to the other. But what language will this conversation use? One which should naturally and more precisely express domain-specific semantics, including units of measure, variability, and connectivity. Conclusion. All the concepts and notations proposed for the initial and transitional languages are intended to be directly transformable into concepts and notations found in the target industry standard languages. Although the extension languages propose some new concepts, it is hoped that these can be expressed using conventional target language conventions, but potentially with less accessible syntax. In our proposal for the visual and transitional languages, we are responding to the key requirements for professional and user programmers to provide a continuous educational trajectory from entry-level programming to proficiency with industry standard languages. In our proposal for the extension language, we are responding to additional requirements within the design computation community for language features which can more directly express important domain concepts, such as units of measure, variability, and complex connections, specifically to support innovation in building systems integration. Each language has a set of key features and associated programming tools to help the user progress through the sequence of languages. While the motivation for these language features was initially a response to the particular needs of the design computation community, many of these features, and indeed the underlying motivation, are quite universal. Therefore, it is hoped that the implementation of these features, initially as a domain-specific language, will lead to their wider adoption in general-purpose languages. The ideas presented here are the result of an ongoing collaboration between members of the design computation community and the programming language research community. In this collaboration, we have combined our analysis of the usability of existing languages with recent advances in programming language research to define a series of tenets as the foundation for the next generation of design computation languages. Thank you.
Let's thank the speaker. There's time for questions. Let's wait until we see, I think, Al and Robert. Maybe could be the Alice there, I see. Static image.
Hello, can you hear me?
We can hear you. We just have to figure out the screen. Here we go. So we have a camera. Yeah, we have a camera from Al, and that's fine. Yeah. So we have a first question.
Okay, perfect. And we should have Robert as well. I don't know if he can be moved across and camera on as well. But yeah, perfect.
Hi, am I on? Yes. Thanks. That was a very. Whoop. Is it gone? Are we still on? So that was a wide-ranging, this is a wide-ranging proposal, and I guess it's a good advertisement for reading the paper, but I would just like to be lazy and ask you,
good opportunity.
Connected collections, is there a string of standard computer science buzzwords you could throw at me that explain what that is?
Yes, perfect. So as we described in the presentation briefly, and then in the paper, my background, so this is a collaboration across computer scientists and then design engineers. So my background is actually as a structural engineer. So be gentle with me. But a connected connection is effectively how we need to represent the physical built environment, so even the building that I'm sat in here, as a digital computational representation. So it's about having that two-way connectivity of cells and walls and nodes and links, and having that full, what we would call non-manifold topological representation. So we have a full shared representation that I can navigate across that graph in all directions, knowing that the cells, who are the neighbors of the cells, they have shared boundaries, and those shared boundaries know the representations of the cells. So that connected collections is something which comes up many times in the built environment for representing neighboring rooms. If I want to model the flow of heat or even people through doorways, we need to know the connections between those things. Equally, it could be to do with a structural system in terms of how a building is standing up. It could be a road network. Any of those, graphs occur many, many times, obviously in an abstract form. What we are proposing in our paper is that a data model or a data structure that can actually represent the connected collection in a way that can be easily navigated by the programmer and the end user, so they can very easily navigate those analytical models without having to, generate those data structures themselves as a one-off each time. So I don't know if that, you want any clarifying questions, but that's a sort of bit of a background to why that's such an important subject for designing, design computation.
Thanks.
So thanks for your talk. I come from both the object design world and the patterns community, and have been involved in writing a number of papers about patterns, about adaptive object model systems, and knowing a lot of more of just the basic design patterns than you might know about. And so from my point of view, there's a lot of techniques. Now, whether you bake these into a different language or not, there are a number of patterns from the adaptive object model papers that people have written. I can certainly pass you pointers to that. But also, the idea is if you have a known set of types, you can sort of, I'm going to say, through a tinker toy way of specifying things, build up more complex types. So anyway, so those are things that could be handcrafted, but if you know them in a language, you could generate them. So that's just one thought. The other thing is, in the pattern literature, there are things like ranges, intervals with different dimensions, with whole value patterns, and that allow you to convert between. And now, those are like, people in the past would handcraft them, but if you're creating a language, you might build some of those in as standard class libraries. Anyway, just two things to consider from that. And if you want to have more discussion about it, I'd be happy to talk about that.
Thank you. Yes, that's really interesting. I think where, as we described in the presentation and in more detail in the paper, it's exactly what you're describing here, that there's a plethora of solutions and ways of representing some of these programming concepts, but serving that to the end user in a way that is actually discoverable, intuitive, and usable on as they go on their sort of educational trajectory. So I think one of the things we talked about there in terms of visual programming is something that has been widely adopted very, very quickly in the construction and design computation industry. And how do we surface, and I think that's some of the stuff we touch on in the paper, how do we surface some of these concepts such as ranges, such as types, such as these things that may exist in other more specific domain programming languages? How could we surface those in a visual programming environment in a way that doesn't, again, become a sort of overwhelming, you need to know 100 things before you can even get going. Right. So I think that's a really interesting area for further. Yeah,
anyway, so I think that's there's some things, but people have built adaptive object model systems that present these to users in ways that allow them to extend the systems as well. Now the other kind of question that I have for you in this.
So let's speed this up a little bit. So we have two more questions. So
Can I just
sure
very quick question? The impression I got was that went from simple, beginning level all the way down. But is that really the workflow of someone who maybe wants to dabble with something a little bit? It always seemed like you were going to the right to more detailed, and I have to know more. But is that really the flow of people working?
I think that's a really good question, actually. And one of the tenets that we've been looking at is actually this co-creation and collaboration. It was actually touched on the previous paper, the Yin and Yang paper, which was really, really interesting as well, that the readability, discoverability, and interpretability of a script or a piece of code that one person has written and then hands that on to another user. So I completely agree. There is this educational trajectory for an individual. We certainly need to be, we would argue, improving the programming tools such that it's easier for a end user programmer to be supported in learning and also effective and efficient and building code that can be verified from early on in their learning trajectory, but it also allows them to progress to more complex things. But equally, they need to be able to then share these maybe more advanced versions of their scripts with people that are not going to spend the many thousands of hours or hundreds of hours becoming an expert programmer that person might have done. And certainly in the design community, that is it's an incredibly collaborative environment where you need people with lots of different skill levels to be able to be effectively operating and using a common tool set. So I think that's a really good point.
So quick last question, I hope. Let's see.
I'll try to ask the question quickly, but it may be a long answer, but we'll say a short one. I work on the second version of the systems modeling language, which is intended specifically to model physical as well as cyber systems. Includes a lot of what you're talking about, including quantities and units, 3D topology, visual and textual notation, working towards full executability, which V1 had. And there's really some big modeling tools coming out, including connecting to also other engineering tools, because systems engineers, this is for systems engineers that have to do overall systems models and connect into all the other engineering kinds of models and computational platforms. I was wondering if you'd looked at that and wondered what the relationship might be, because even if you're looking for more connecting into programming environments, you might be interested in the work that was done, for instance, in taking the entire ISO specification of all the SI units and providing a complete model of that. We actually have a complete model of that, as well as of 3D and 4D modeling.
That would be, that would be very, very interesting. I'm not aware of that, and I'd be keen to hear more. One of the pieces, again, that we touch on is in terms of this challenge of interoperability, of connecting many different tool sets together. There's a vast variety of different tools that need to be used, in the different domains that come together in the built environment. So, almost by necessity, we need to be, using these multiple tools, but learning from them as well. So I'd be really interested in that, actually. That sounds fantastic. Thank you for that.
Happy to get in touch. If you Google SysML V2, SYSML space V2, you'll see, get a bunch of information about that.
Maybe you can both, Rebecca, also share some info on the Discord. So give him an URL or something, and then you can look it up there. So, or an email, right? So whatever works. So thank you. Thank the speaker again.
Thank you so much.
So we see each other again after lunch. Thank you.
to my highly directional microphone. This is the last Onward Papers session of Onward 2024, and following it will be the last essays session. So our first paper is being presented remotely by, I believe it's Christoph. I can't pronounce his last name. What is it?
Christoph Tiede.
Very good. A directional microphone. Okay, are we all set? Let's go.
Okay. Yeah, thank you for the kind introduction, and welcome to my presentation. Hope you have a nice weather in LA. And in the beginning, I'm talking a bit about what is exploratory programming at all, because if we want to talk to objects in natural language, then we need first to define what this is. So we are talking about programmers who want to work with exploratory programming systems, and we want use objects in different systems, and we want to ask questions about them. So our goal is to develop systems iteratively and to understand how systems work. And for this, programmers might have different questions, such as what is this object about? How can I invoke this feature? Or why does something not work as expected? And to achieve this, the programmers can interact with the objects in the different system. And for this, they need to perform a lot of technical experiments. And this can become pretty complicated because all these experiments require technical tools and writing code and verbals and things like that. So
Christoph,
this can
your
lead to a lot of
slides,
complexity. And
the slides are still on the title slide.
oh no, this is very wrong. Okay. It says it shares my entire screen. I will reshare it. Can you see it now?
Yes, we're on motivation. Page 9,
And
10?
now another title?
Page 10.
Okay, so I hope that it's updating now. Okay, so where had I stopped? So I was talking about the complexities of experiments in when interacting with objects, because we have technical interfaces and we have a lot of complexity in communicating with the objects in the system. And also the results can be complicated to understand, and all of this creates a lot of complex experiments and technical overhead in the process, and also cognitive overhead in programmers. And on the other hand, we already see in different areas of software development today that there are already generative AI agents that support programmers at different tasks that are related to comprehending or interacting with source code. So we wondered, why can we not also use such agents to support, to streamline and augment the exploration of objects? And this leads to our proposal. Here's a sneak peek of it. We propose an exploratory programming agent.
Christoph, your slides are still not advancing.
Okay, I will try something else. Sorry for that. I hope it works better now.
Okay.
And then now, yes?
Yes.
Okay, then I hope that it works this time, and I apologize. Okay, so we propose that we have just an exploratory programming agent which sits between the programmer and the system and allows programmers to ask their questions as natural language questions, and then the agent can perform all the required experiments on their own, and finally provide the programmer with another high-level natural language answer. And formally, this leads to our research question. Can you still see the new slides now? Slide 13?
No, we're still on 11.
I have no idea why this is happening.
Now it's 13.
Okay, so, well, maybe we just have some delay. Okay, I just will hope that it works. So our research question is, how can we support exploratory programming through semantic object interfaces that enable contextual natural language conversations with or about objects? And for this, we make three contributions. First, we propose a framework for semantic object interfaces. Then we present our prototype for using this framework in a Speak Smalltalk context. And finally, we evaluate our idea based on our experiences. Let me now give you some extended background. I hope to now are on slide 15 as well. Can you see slide 15?
Can you maybe not use full screen?
Yes,
For the
slide
slide-
16.
for the
So
slides.
I hope it's still up to date. Okay. And so it gives you a more precise definition of exploratory programming. We define this as a setting where programmers understand problems and systems iteratively. And in this process, they work like researchers by formulating questions, conducting experiments with the system, and evaluating the results. And we can have them tell them to have conversations with the system in this process because they perform so many small experiments and ask questions to the system. And it is important that we can make this conversation, Nils-style, vivid and extensive. And to achieve that, there are different exploratory programming systems which support some kind of liveness and just short feedback cycles to allow for frequent experiments. There are different examples of such exploratory programming systems, such as operating system cells, such as computational notebooks, or different Smalltalk systems, all of which provide different interfaces and tools for different activities, such as including domain-specific and task-specific tools, such as code browsers or debuggers. But all of these tools have in common that we need to ensure that we have that liveness and that feedback cycles, and to enable that, we have the challenge of making sure that programmers can really convey their intentions to the system. And this can be pretty complicated, as can be seen from this model with the two gulfs of human-computer interaction. So on the one hand, we have the high-level goals or the mental model of users, and on the other hand, we have a physical system or the technical implementation. And whenever programmers want to convey their intention to their system, then they have to gap this gulf between these two, which is called the gulf of execution. And also to understand the results of the system, they had to interpret the display, the results displayed on the screen back in the mental model. And so this creates a lot of semantic distances which can hinder effective exploration. And on the other hand, as already mentioned before, we already have different applications of generative AI for programming. Most of you will have used something like GitHub Copilot for code completion, but there are also other tools such as conversational agents for IDEs or code review tools. But all of these tools are very code-centric, so they mainly neglect any available runtime information. And so this leads to our approach. We propose a semantic object interfaces framework where programmers can ask functional and epistemic questions, so they can ask high-level conceptual questions about objects in a system, and they do not have to perform manual experiments, but instead they can ask these questions to an exploratory programming agent, which then automatically plans experiments and evaluates and iterates as necessary. And internally, only this agent then interacts with the system by inspecting the state of object, browsing the implementation of objects, or sending messages to them. The agent also has access to a list of policies that describes its behavior, and also to a conversation history to allow for all the questions being asked in the context of former questions. There are different types of questions. Functional questions are about the state of domain objects, such as in a shop system, for instance, you could ask when an order was created, or epistemic questions are about the behavior of objects in a system, such as how does the ranking in a shopping system work like. Okay, and given that framework, we then can think about how we can actually provide these semantic object interfaces in exploratory programming systems. And for this, we have identified two different interfaces, two different starting points that programmers frequently use when they want to explore objects. The first one of them are object inspection tools, which regularly display something like a list of variables and properties. And to this, we add a new conversation mode, so programmers can also, instead of just viewing the raw state of object, have a high-level conversation with the agent about the object. There's also another frequent starting point used for exploration with the scripting. So we often have something like a REPL or a debugging console where programmers can type in technical commands, or in object-oriented terms speaking, where we can send different messages to domain objects. But this requires an understanding of the precise vocabulary of these objects. And so instead, we propose an extension for the scripting languages for semantic messaging. And so I can just write some kind of pseudocode here. But the important difference is that these semantic messages are not implemented on the domain objects, but instead they are handled by the exploratory programming agent, which will then conduct its own experiments and finally return the answer as another regular code object. Okay, so these are two possibilities for integrating semantic object interfaces. And now I give you a brief overview of how we implemented our programming agent. For this, we used the large language model GPT-4o. And what we basically did was creating a large system prompt where we describe the expected behavior of the agent, including things such as the identity of the agent and the expected output formats. Something interesting is that the LLM by default is very lazy and does not perform a large number of experiments. So we stimulated it to more exploratory practice by including a larger number of experimental samples within the system prompt. Also, we need to provide the LLM with access to the system, for which we provide different functions for evaluating code about the object, or also for browsing different classes, packages, or references of methods in the source code. Okay, so this was a short overview of how our approach works and how we implement it. And now I'm switching over to give you a short demonstration of it in action. And I hope that we will have no further problems with screen sharing. So I hope you can now see a different window. And here I'm in my Squeak image, and I have this order object here from a shopping system. Could anybody just quickly say that they are seeing my demo?
Yes, we can see it.
Perfect. Good. So we have an order object here, which is something from a shopping system. So you might stumble upon this in any context, just as debugging a larger issue. But for now, we just want to know when this order was created. And to show you how complex it is to answer this question with traditional tooling, I will just try it. So we want to know when this was created, so we can take a look at the different variables here. This one is probably not relevant, so I can take a look at this properties object here and find some other state nested in it. And finally, here is some kind of number for the creation date, but I cannot really say what dates it represents, so I need to convert it first. So I can try out some scripts, such as assuming that it's a Unix timestamp, use this conversion code, but it does not make sense. This object was surely not created in the year 56,000, so maybe this is a Unix millisecond timestamp. So I divide by 1000 and finally gets the correct answer. But you can see that this involves a lot of technical overhead and different tools and interface being used. So I instead can also use a chat mode, which we have integrated here, and ask instead in plain English, when was this order created? And then the agent starts to analyze the situation by itself, finds out everything what we have found out before, tries out different conversion methods, and in the end, it has found the, so we can see all the different steps in the code it evaluates. And I have to say, sometimes it works faster, sometimes it works slower. And in this case, we finally have the correct answer here. Often this works faster, but even in this case, you could see that I just have to type in a single question and wait for a few seconds instead of using all different tools manually. This was just one example. Give me another one where we have a formatted text object, which is used in Squeak for using different attributes for adding emphasis to a string. And now I'd like to understand what this object represents and how I can use it. And for this, I can again go into this chat mode here and ask something like, what attributes do you have? Note that I also can talk to the object in the second person. And then the agent finds out that we have different emphases with the code 1 and the code 4 here. And then I wonder, what is this code? What do these codes mean? And so I ask, what do these codes mean? And the agent starts researching the different documentation artifacts available in the system and comes up with this summary. And finally, I also wonder how we could, for instance, change the attributes of this text. So I could ask another question like, give me different code samples to make this all italic, and then the agent starts to research the available protocols on the text object and comes up with, for instance, this example here where we use the add attribute from to method. Okay, so this was about the demonstration, and in a sense, you could see that we can use different can ask different questions to explore the state of behavior of objects here. But we wanted to go further. We did not want to only support object inspection, but also provide semantic interfaces for other programming tools. And for this, we made the observation that many softwares, not even only programming systems, have object-oriented user interfaces. So you literally can see the single domain objects on your screen. And for this, we proposed that we can add a generic UI mechanism that allows programmers to click on one of these domain objects and then have a conversation with them through the exploratory programming agent. So the individual software does not need to provide its own agent, but instead the exploratory programming agent will find everything about the concrete domain and the required interfaces on its own. And then we can see that many exploratory programming tools that we have today already employ object-oriented UIs. For instance, code navigation tools provide access to the different meta objects such as classes and methods, or editors provide access to the different nodes in the AST of a method, or debuggers provide access to the different parts of a process. And so we can use our generic UI mechanism here to talk to the different code artifacts which we can see in the programming system. For this, I have another short demonstration for you. I'm opening a debugger here where you have a typical situation of seeing a complex call stack with a lot of methods and a lot of variable and other information. And I have just a simple question about a single parameter here, and then I would like to know where does this come from, what is this about, what does this fail block here actually do. And for this, I can switch into this chat interface here and ask what is fail block from, and where's fail block from, and what exactly does it do. And when I ask this question, then the agent starts to investigate all this call stack and additional information, and comes up with an information about the different methods where this could be from. Or I could also ask what exactly will it do to further stimulate the agent to find out what the block does itself. And finally, we also get this information. It attempts to visually flash the editor and the compilation, if the compilation fails, and this is actually correct. Okay, so this was about the demonstrations, and now I'm moving over to the discussion. We discuss our idea first with respect to the feasibility of our agent, and second with regard to the impact on the exploratory programming experience. Let me start with the feasibility. We see two things here. First, we take a look at the limitations of LLMs which affect our agent. We could see that in some situations the agent would provide errors, so it would hallucinate or would conduct incorrect reasoning. And second, we also see some failures. We have seen in some of the demonstrations insufficient answers where I had to reiterate and ask follow-up questions to get correct answers. In other situations, the agent would just never end to experiment. But in general, we think that these are no systemic limitations, but can be improved by training a large language model for specific abilities, such as working with this Greek Smalltalk framework in our context, or working with exploratory practices. We also have some performance considerations. For simple tasks, this is usually not a large problem, where we have pretty small delays and financial expenses, but in more complex situations, delays can increase and monetary costs can too. If we, for instance, use the agent for an entire hour, we could spend as much as $60, so surely some further optimizations are required here. But the good news is that we have some ideas to improve the performance situation by fine-tuning a smaller language model or optimizing the prompts. So our current prompt is, if you print it in paper, which I actually did for my thesis, a couple of pages, and I'm confident that this could be shortened to improve the performance. Second, we have the programming experience, and here we can notice that semantic object interfaces provide a higher abstraction level, so we can reduce interruption and cognitive overhead for programmers while improving the semantic immediacy and the flow of programmers. But like many abstractions, also semantic object interfaces can eventually leak when the agent fails. And in this situation, the programmer needs to start all over again and take a look at the manual manual artifacts that they have tried to avoid and learn about before. And also there's a risk of missed serendipitous discoveries. For instance, when you are manually searching for a method, you might scroll through a lot of source code and learn a lot of other things that you might need later. And such discoveries do not occur when you use an automation for the search instead. Because semantic object interfaces have a natural language interface, we also can reduce the gulf of execution and evaluation by avoiding technical interfaces, and conversation history allows for asking questions or asking follow-up questions in the context of former questions. Mentions the limitations of language models, which lead to a limited trust in their agents at this moment, which can create larger temporal distances. Sometimes it's just too expensive, and there is also the danger or the problem of using too much energy and water. So, for instance, if you would use our agent for an entire workday, depending on your region, you might spend as much as several hundreds of liters of water. So this is certainly something which needs further attention. Finally, some ideas for future work. I already mentioned that we need to improve the capability and the performance of our agent. And another issue which I think is even more interesting is researching other ways to improve the collaboration of programmers and exploratory programming agents. So at the moment, we have something which is more or less automation, but it's important that we also keep programmers in the loop. And one way to achieve this could be to improve the explanation of the steps and the answers of the agent, so that the programmer can also continue on the steps of programming agents, even when the answers were not yet perfect. Okay, to quickly conclude, we have proposed semantic object interfaces that allow programmers to ask high-level semantic questions about objects in a system and answer them through an exploratory programming agent. We have provided different ways to integrate them into programming systems through different tools and through semantic object interfaces and through semantic messages. We have presented different applications for different tasks and domains of our approach, and finally found out that semantic object interface improves the semantic experience of programmers, can reduce cognitive overhead, but at the same time can also reduce the opportunity of serendipitous discoveries. Finally, we see that we need to optimize and fine-tune language models for exploratory programming specifically. Thank you a lot for the attention. I hope I have not too much overtime from the technical problems. And after the discussion time is over, I'm still happy to take any questions on Discord.
Thank you, Christoph. So we do have time for questions.
That's great.
You need to speak directly.
Right into the mic.
It's highly directional.
Highly directional. Hi, thank you for the talk. This was very interesting. I had a couple of questions. First, I think you mentioned during the talk that your agent can execute code. Is that correct?
Yes, exactly. So I mentioned these three kinds of experiments that the agent can execute. One of them is inspecting state, and sending messages is another one. And sending messages essentially means to generate and execute code on its own. Yes.
I see. Okay, I was going to ask, are there other tools that you make available to the agent? Like, can it grep through the source code, or sort of the other suite of tools that you typically see for software agents, or is it just the execution?
Well, it's more than execution. So browsing the implementation essentially means that the agent can take a look at the comments and yes, basically at the comments or at the organization of source code. So it's more than just accessing, more than just generating code.
Okay. And then I think the second question is kind of related, which is, how do you construct the context that you give to the model, I guess at the very beginning? It sounds like the model can do some exploration on its own, but do you sort of preemptively decide, hey, you probably want to look at the source code of the object, or what do you provide in advance, and how did you decide the breakdown between what you sort of proactively show the model versus what the model can query for?
Yeah, this is very, very interesting question, and there's a lot of research going on prompt engineering in general. So what we do first is we have just textual explanation which describes in great detail how you should look at objects by sending messages and so on. But specifically, we something like in the beginning of each conversation, we run some first experiments for the agent. This includes just getting all instance variables of an object and getting a textual representation of the object. And this is some initial context. And something else which we can do is that we, for specific domain objects, such as in the debugger context, we also provide some other information. So in the debugger context, we actually pre-generate an excerpt of the entire call stack. So the agent is just like this. Suppose the agent already sees some relevant information without needing to perform initial experiments on its own. Does that answer your question?
Yeah, that does. Thank you very much.
I have a question. I may have missed it in all the confusion, but what's an example of a serendipitous discovery?
Yes, okay. So the idea here is that when you work with the system on your own, you just see many information. A lot of them are not relevant, or at least not immediately relevant. But at some point in the future, you might remember something you have seen by accident. So one example of this, if you want to find a message that solves task X, you scroll through all messages in a class or in an object, and 90% of them are all irrelevant, but just by seeing them, you already form some kind of mental model of the capabilities that the class offers. And later you might remember some things, and you can use them later for doing any other tasks, or you read some comments that teach you something about the internal implementation. But if you automate this, then you just do not learn anything about this at all. So you just get the final answer, and when you later need another information or in another context, you do not have it or have to ask for it separately.
Okay, so what is the most surprising result that it gave you in your experiments?
A lot of things have happened. One example is that I had a tool for accessing commits from GitHub, and I asked the agent about this tool object. Can you please give me my API key? So the task was that it was just a configuration for the relevant entries. But then it said, sorry, I cannot provide confident information, which does not make sense in this context. But it was very confusing in the beginning.
Okay.
Something else was more like that the agent would never stop, so I asked it to visualize some dictionary, some table of data, and it was almost there, but some numbers were offset, and when I asked it to correct it, instead of correcting that, it came into some loop of correcting itself all over again, and in the end it questioned basics of the language syntax and spent $10 or more before I stopped it after 10 minutes. So it completely lost the track here.
Okay, thank you. So, are you ready? Next up is Philip Strombach.
Close enough.
Active DSU, Dynamic Software Updates for Active Functions.
Thank you. So, to set the stage for this idea is, imagine you're writing some kind of simple threaded application. So you want a thread that processes messages, incoming messages. Doesn't really matter what they are doing at this stage. We have a message queue, we get messages, and since I'm developing this thing, I'm printing them out before I process them. And assume that eventually, either if I'm in a live system and I'm like exploring Onwards, or if I have actually deployed that one and want to change it, I want to update it so that I want to be able to send messages to threads to ask them to exit. And I simply do this by adding some methods to this object. And as you can see, I set an exit flag in the loop. And interestingly, I also have some logic to try to migrate any remaining messages to other threads towards the end. And there are techniques that will kind of allow me to do this, and I can use dynamic software updating for it. And these are useful both during development, because you can do quite flexible live programming with them, as we shall see. And we can also use them in production. For example, if I want to apply this thing without having to shut down my program and start a new version of it, for example. The interesting part about these two things is that while like the mechanisms are similar, there are slightly different requirements. For live programming, for example, you want minimum effort in order to be able to apply an update, because otherwise it's not worth it. You can just restart your application. While in production, it's very important that the update is correct, because otherwise my program will, or the updated program will crash in production, and then I'm very sad. In this talk, it will be a bit more geared towards live programming, because as you can see, it's a bit experimental at this point, but I hope to be able to get to something better. In particular, as I've written down there, we need two major things in order to apply an update. We first need to think about any changes to data structures on the heap, for example. And we also need to consider control flow. This talk will focus on the second one, because there's quite a lot of research in the first, and we can actually use that, as we shall see later on. And the goal I'm proposing is, as the title says, active DSU. So the goal is that I want to be able to update these things without waiting for something to happen. And to be able to do that, I need to be able to update active functions, that is functions that have stack frames on some threads stack. And ideally, I want to be able to support large set of updates, few annotations, and with minimal runtime overhead apart from the actual update. The first thing we should think about is, where do we allow updates to happen? If we imagine that we just pause a program at any point and look at the call stack, what we will see is that all stack frames except the topmost one will have execution paused at a call site. And this is nice, because then we only have to consider call sites. Call sites are quite nice in the ABI also, because they are kind of well defined in where things can live due to the ABI. But for the topmost function, we can pause essentially anywhere. However, if we allow ourselves to execute some bounded amount of code, we can advance the program until we get to a call site or a back edge, so that we get to a loop header. And that way we can reduce everything down to that we only need to consider call sites and loop headers, which is much simpler than anywhere in the program. So for the example that I will be using here, let's just consider that we will be updating the program when we are waiting to get a new message inside the get function. And that is good enough for our purposes here. The first step we can do is as simple that we need to simply relink the program. That is, we essentially run the program through the linker again, but in process, of course, which sometimes needs some kind of interactions and stuff. This would kind of work, but what will happen is that for active functions, for example, the main function here, when we return from our get function, we will return into the old version and continue running there. So what happens is that we won't see the changes I made to the main function. However, it will, of course, call the new versions of get, debug, print, and process if I change them. So this is like the fundamentals, but it won't really solve this particular problem of active functions. An interesting solution, or partial solution to this one, is from the tool that's called Ginseng. It actually automatically extracts loop bodies into separate functions and uses the same approach. And that way, we get this interesting behavior that for the first message that we receive after the update, we'll run the old version of the loop body, but then we will return back to the main function that is down to the left there. And then on the next iteration, we will enter the new version of the loop body. So we kind of get into an intermediate state between the two versions, because as you can see, since I cannot change the main function as it is there, the call to migrate will be skipped. And there's also some problems with as it is implemented, we cannot really add the exit variable. We can, of course, refactor the loop body to fix it in this particular case, but not in general. One way to avoid this kind of difficult to reason about behavior of these, like just relinking, is that we can wait for quiescence. Essentially, we wait until no updated functions are active, and then we apply the update then. That makes everything much easier to reason about, but waiting for quiescence is in general unbounded. And in this case, we will not reach quiescence because we updated a function with an infinite loop in. So we cannot use this to update this active function. Another interesting solution is to introduce update points, which is done by a couple of tools, either by manual annotating your code by saying, this is a safe point to update in, or by some profiling. The downside of this is, of course, that you need to do some like preparatory work. Imagine in a live system, you don't want to be very much upfront in order so that you can actually be able to continue exploring stuff. So that's the main downside with this thing. And also, depending on exactly where you have your update point, you can get these kind of delayed updates. So for example, assume I have my update point at the dashed line. I will get similar behavior to Ginseng is in the sense that we will run the old version first. Then when we get back to the next version, iteration of the loop, we will kind of save the relevant state, shut down the program, start it up again, and reinitialize everything. And then we can continue running the new thing, which is not exactly what we want. And you can imagine there's all kind of interesting code that we need to run there and so on. And I would prefer to avoid that. So to get to the solution finally, remember that our goal is essentially that we want to get, when we return from the get call, we want to return into the new version of the function directly. And to do that, we essentially need to rewrite the call stack. So what we want to achieve is that we want to go from the call stack on the left to the call stack on the right. And what makes this difficult is that in this example that I have here, I need to introduce a variable there. So I need to grow that stack frame. And to do that, I need to move the other ones upwards. And of course, I could just memcopy it, but it wouldn't work because, as you can see, I have many pointers to stuff on the stack that will be incorrect. And I will need to know all of them in order to be able to do a good job here. And that's quite difficult. One way is to do as the tool upstairs that injects code to essentially serialize the stack into a separate representation, modify it, and then like reinstall it in a sense. But that introduces quite a bit of like extra code. And again, you need to be upfront by tooling. So what I'm proposing in ActiveDSU is that instead, why don't we just replace the return pointers on the stack? That's actually quite easy to do because the ABI essentially mandates where they are. If you look at exception handling, for example, the dwarf standard says that the variable offsets are specified in relation to where that is, so it's quite easy to find. So once I've found them, I can just replace them with a pointer to a stub that I generate. And what happens then is that this stub will essentially act like a callback from the system for when we would have returned to the main function. And the nice thing about that is that when we return to the main, or when we would have returned to the main function, that one is the topmost on the stack. So now it's quite easy to actually just grow the stack frame, rearrange the variables, and then we just jump to the new version. So I have an animation for it, of course. So I can just add the exit variable, and then finally I jump to the proper location in the new version. And this is quite nice also because after the update, at no point I execute old code. So I can remove it immediately, and in essence, I'm sure that no old code runs so that in case I have modified any heap data structures, they won't be touched by old code. Then the question is where to resume. And for that, I have an idea of call site mapping that works at least for comparatively simple cases. The idea is that I extract a very abstracted version of the control flow of the function. And remember from the start, we really only need to consider function calls and loops. So that's the only thing I have in these abstracted versions of the control flow. And as you can see on the left, we have something that calls the constructor of a message queue. Then we have some loop which calls get, debug, print, and process. And what I do is that I essentially run a version of the diff algorithm on these. It's recursive because I have nested lists and all that. Details are in the paper. But it will produce a mapping like this. So in essence, if I updated the program during the call to debug print, we will just return to after the get function and resume from there, for example. And this is what it looks in the source code that we are in. And at this point, at least with this kind of small changes, is quite intuitive, at least. So the big question is, does this work? And to answer that question, I implemented a prototype. And I implemented in a language platform that I have developed that is called Storm. It's an interactive system. And the language we're using here is Java-like system. Actually, this code is in that language. It's compiled language. And this is important because it kind of feels like Python when you're interacting with it. But it is compiled, so I'm actually doing stack rewrites. I'm not cheating by just putting everything in a hash map and calling it a day. We have garbage collection, so I don't really have to worry about when I deallocate stuff. That's a simplification. And it already had support for relinking programs quite cheaply. So I kind of got the first step for free, or because I implemented it before. And by adding active DSU, I'm now able to update active functions, and I'm doing like simple migration of data. We could probably put in some more complex methods from like other more sophisticated tools and so on to make it even more competent. And I should mention that for now, I only do non-topmost functions. It's just a matter of engineering, not an inherent limitation. And what do I need to be able to do this? Well, I have essentially implemented it inside of the compiler process because it's an interactive system. But as you can see, I have drawn it inside of the, together with a new function, because what it takes as an input is a quite detailed description of the new function, like low-level intermediate representation. It has access to all type descriptions and the compiled version of it. But from the old function, I don't get that much data. So this kind of opens up for me to look at a binary with the debug information and kind of update it there. So the metadata I had and needed to add was information about all the call sites. I kind of had that because I garbage collect these, so I need to update them. I had to add information about back edges, which you can find by disassembling the code in binaries. And I added information about named variables so that I can shuffle stuff around on the stack. But all of these should be possible to extract from a binary if you have debug information at least. And with that said, I think I can try to show you this prototype in action. So what I have here is that I have a small implementation of the code that we saw. And if I start this one, you can see it starts iterating, and it's printing debug print when I call debug print and process things. And the messages are just numbered, of course. So what I can do here is that I can modify it to the last one. It's just a macro in Emacs, it's nothing magic. And then I can ask my system here to update this one. And let's say that all messages above, what will it be, like 35 or so, will be exit messages. Let's do 40. And then I tell it to update. And now you can see it continues running, no debug prints. And then we exit when we expected to, and we even got the call to migrate in as we expected to. So the approach works, at least for these simple examples. And just because I got a review comment about recursive functions, of course, we can do stuff with recursive functions also. So this is just, this log begin is what prints stuff. And as you can see, I've completely forgotten to do the end condition. So if I add that on level 20, yeah, that's fine, and update it, we can see that it continues running until we get to 20. And then we terminate as expected, and we even got this log end call as we would have expected. So this kind of works, at least for these simple examples. And I can just quickly give some details on how this particular implementation of a stub works, because it turns out that you have to keep, like, it's a bit tricky to get it right, especially if you want to allow exceptions to go through functions that are replaced with stubs. But essentially what I do is that I first update the stack frame to get some extra data so that I can spill registers and so on, so I don't have to worry about preserving all the registers. Then I can initialize new variables, and at this point I can call constructors, I can do whatever I want because I have spilled like dirty registers and stuff. I can initialize temporary variables, because in some cases when you're in the part of an expression you have like temporaries that are pointers to a variable or something. And what I do in this particular implementation is that I actually copy initialization code from the new function until I reach named variables, and that kind of gets these past the address of a variable to the function to work. This is not perfect. There are cases I know it will fail. And then when I've done that, I can just restore the registers, shrink the stack frame back to the new size, and then I can just jump to it. So what is there, how to say, left to do? Well, as you can see, this kind of idea opens up to much exploration of what we can do, and in particular, this like trade-offs between how much should we do and how much gets confusing for programmers. This particular example I have here is probably an example when it works good, but you can imagine if I simply replace the entire implementation of a function with a new one, then one question you should ask is, what should happen in that case? And the second question is, how much can we do? Because in general, we cannot really solve that problem. And related to that is like, how can we show to users how they can reason about what happens in updates? And that's particularly important if we want to do it in like production systems, of course. In live programming, I mean, in my opinion, the worst that can happen is that your program crashes and you have to restart it. And we're still like kind of winning if we can have a 90% solution there in live systems. And then finally, it would be nice to combine this with more sophisticated approaches for like intelligent migration of data, but there are related work for that. And I would like to explore an implementation in Clang and C++, because like imagine taking a binary with debug information that the author didn't prepare for me, and then I can just run Clang and give it some kind of patch that I can apply. I mean, in essence, I don't see anything preventing that from happening, but there are things that will need to be worked out. So to conclude this idea of active DSU, we can update active functions. We can do quite a lot of things, and opens up for exploration. We can do quite interesting things in this space. And I don't need extra code in either version, so the steady state execution is not impacted. The only cost is when we actually shift between these versions. And we can even do quite a lot of this like ahead of time. I don't have to have all the implementation in the like live system. And some details on exactly what needs to be done is in the paper. I can also mention that it's available at the website for the system. But I haven't done any precompiled releases yet, but you can find it in the branch that's there if you're interested. And that is everything from me, so I'm happy to take questions.
All right.
Hey, thank you for the talk. What happens if you make a modification that basically changes the past? Well, use this recursive example. You made the change just as quickly enough before it reached the 20. What would have happened otherwise? Well, if your return is not there anymore, right? Where to return to if you remove the call?
You mean if I remove it, what the current implementation does is that it will map it to the start of the function and just run through the function. And what you're getting into here is a discussion of, first, what do you expect would happen? And then the question is, what should the system do?
Well, I'm experienced with Smalltalk and Squeak, and well, you update the topmost function, right? And everything else is the old version, and this seems to be working pretty well. Of course, it has limits, so, but I can't get my head around rewriting the past, so I would not know what to expect. So
exactly.
what the stack would look like.
And this is also an interesting observation, is that even though I changed the recursive function, of course I'm not rewriting the past. The call will still have happened in the sense. So for example, assuming that I make the condition on the recursive thing after 20, as you said, the call to 24 would still have happened. But what will happen is that once those calls return, the active DSU will find a location to resume from in that function. And if you have removed the call entirely, then it resumes from the start of the function in the current implementation. If there is a call, even though you didn't execute it, it will appear as if it returned from that call. So that will still give some unexpected things would happen in some cases, but it's still better than mixing all the new code in greater extents in some cases, I think.
Thank you.
Thanks. Am I on? Am I on? Yeah, there we go. I really enjoyed this. It's been a while since I read about ginseng and upstairs and all the rest, and I was thinking during your talk, so there's always a bunch of assumptions about, what cases are known not to work, and there's often a bit of fuzzy areas like we don't know if there's things in this space where we haven't really articulated what will work, what won't. The thing I was thinking of is if you have, if in the stack frame that you're resizing, if you have incoming pointers to that, maybe because you let a pointer escape earlier in the execution, can you deal with that? And can any system deal with that?
Yeah, that's actually a limitation I mentioned in the paper, but I tried to keep down to the allocated 15 minutes in the beginning. I failed and get 20, but it seems to be fine. But that's actually one thing that is nice about this language, is that I don't allow taking pointers to stack allocated objects, so I'm kind of saved there. I still have the issue with if you're returning a bigger data structure, the way returns works in many ABIs is that you have a pointer towards it, and you have to deal with that. And one idea that I have is, and I haven't tested this yet, is because you kind of know when you get pointers from that have escaped by parameters and so on, at least if you think one levels as a start, you can kind of detect that and allocate them elsewhere temporarily, because when such things will have changed, you kind of get the chance in both functions, or at least you can arrange to get the chance to fix it up in both functions. But we are talking about a can of worms here, as we are into. And that is a challenge with moving to C++, for example, because there you do it quite a lot.
Right. I would love to talk about this later, or actually remotely, because I'll have to dash off after my talk. But thank you. This is really good.
Thank you.
So this is really great. I congratulate you on the explanation of the related work. It's always nice to have that introduction, because the audience usually isn't as up on it as everybody else. And I also want to congratulate you on your courage for trying to make this work. It's really crazy, right? So
my friends tell me that when I show them this.
So my particular scare was when you showed diffing of the text before and after. And we all know that when you do a diff in Git, it can get it totally wrong, right? Especially if you're moving code around.
Yep.
So my question here is twofold. One is, do you experience those problems? Do you have any solution to it? And second, have you thought of, instead of doing textual diffing, using a structure editor, which can give you, much safer information about how the program actually changed?
Let's start with the second one, because that's what I remember most. In a sense, I'm not doing straight line text diffing, but in an essence, that's what I'm doing, because I'm looking at the artifact of compiling the text. It would be very interesting to have this.
But that's even worse, right? Because now you're diffing the output of the compiler.
Exactly. But what you're saying is, if you have input from a live system or from the editor, from the history there, that would be great in these kind of situations. In the system I showed you, I do have Emacs integration, but it's only like talking to the compiler. So I don't have that currently, but I think that would improve the situation if you know what has actually happened. So that is a great idea to improve this. But for the like textual diff with like things misbehaving, let's just call it like that, it goes into this idea of some changes are too large and we're never really going to get them perfect. But there are certainly better algorithms that handles more cases. And I mean, this works for kind of simple cases at least. That's like the extent that I have tested it to so far. But there are certainly edge cases that I can improve with that. So you're completely right in that it will make mistakes in its current form at least. And I will have to fix those.
All right. Future work, as they say.
Yeah, exactly.
More research is required.
That's why I have this.
All right, let's thank the speaker.
Thank you.
Yes, we are. I'm going to take the poo break. Okay, that's fair enough. All right. Can someone cue the background music? All right, email break. Are there any stand-up comics in the audience that would like to entertain us? Oh. So Stephen Kell is going to talk about source level debugging of compiler optimized code, ill-posed but not impossible.
You spoiled the punchline. I left it as dot 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 because I know, but look, I left it out. It's fine. Okay, am I good to go?
I believe so.
Okay, thanks. So, as Jonathan says, I'm Stephen. This is joint work with my student Ryan Stinnett. And yeah, we're talking about source level debugging of compile-optimized programs with an elided punchline, which we'll get to later. So this is the problem that we've been thinking a lot about in the last couple of years. Who has seen a message like this before? Variable optimized out. OK, a few hands going up. So this message is really lying to you. It's the debugger saying that a variable's been optimized out, but what it should really say is, well, I don't know. Something has happened to this variable. There's no debugging information for this variable. I assume it's optimized out. But in practice, it might well be that variable I is living happily in your program, or an illusion of variable I can be reconstructed in your program. It's just that the relevant debugging information somehow went astray or got corrupted or so on. So what we're thinking about is how good is it possible to make the debugging experience given that our program has been optimized by the compiler. I'm going to attach a slightly pedantic side condition that might pay off later, which is that what I also want is that we're not running our program in a special debugging environment or a special sort of harness or tool or interpreter. When it starts running, it really starts running outside any debugging, and the debugger might not yet be attached, and we attach it later. The whole point of this paper and talk is to kind of try and change people's minds about what is possible. So we spend a lot of time staring at stuff like this. Please don't stare at it too much. It will hurt your eyes. But this is some of the debugging information that comes out of a C compiler if you compile a Hello World program and you ask the friendly readelf tool to dump it. In short, it's a lot of very detailed information about how the compiler has realized your program at the binary level, and it's sort of relating it up to source level. We're going to think about things instead in terms of transition systems. So it's not in a formal way, but we like to have a nice mental model for what's happening in our program. So this is a little piece of a transition system of an imaginary program as viewed at source level. And what I've just done is created a state where in each state we label the state with the concrete values of every variable in the program and the program counter. And we should, for fullness, we should also be including the stack and the heap and whatever state there is in the program right there. It all gets labeled on the state, and then our program moves from state to state as it executes. Okay. This is mostly very deterministic, and it's only when we take some input, like here I did a get char, it's only when we do some kind of input that we actually have any branching in this transition system. So that's our mental model for how we're thinking about what's going on with debugging. So obviously, that was a source level view, but we can write the same thing out for a binary view, the actual compiled program. And in this instance, it looks kind of the same, except that, well, where we previously had a program counter, now we have some, register holding a, we had a source level program counter, now we've got some register holding like memory address, whatever, and all the local variables have become sort of registers and something. And then the atomic operations that we're doing are no longer source constructs, but they're things like, move this value from register to register. And the only difference we've got in this very simple example is that, well, we previously had 4 states, but it turned out on this machine we need 2 instructions to do an if. We need, the compare and then the conditional branch. That's a really simple case. But to make this debuggable, we need some kind of function that's going to map up from that machine state to a source state at runtime. And here we've got it easy, but in general, if the compiler has done a lot of complicated transformations, then we're going to have to somehow undo or see through those transformations in order to present a source level view. This is a really, really hard problem in general, right? So we can draw some pictures a bit like this. I'll have a few of these. And this is just kind of what we've seen already. We've got the blue circles that are the object level states, and we've got the orange ones that are the source level states. And at certain points, we may have a mapping where we can say, OK, this state corresponds to this source level state, and so on. Or we may not have a mapping. So a little interlude now, because people always ask this question. Who cares? Because why not just recompile without optimization and then all our problems go away? Well, you can do that sometimes. I see that as a workaround. It's not really solving the problem. And there's a few reasons for that. One is that when we say debugging, it's kind of a shorthand. We don't mean just debugging. We mean any dynamic analysis that wants to present results at source in source terms, right? So it could be a debugging, could be profiling, could be tracing, where we want the program to run really quickly. We don't want to interrupt it and sort of step through things. We want to keep running, and then we collect some information that we present at source level. We can use the same debugging information for that. It might be a program that just doesn't work if you slow it down, right? So it could be a game. We talk a lot to people at Sony who work on the PlayStation tool chain. And it's also for this annoying reason that sometimes optimizations really mess with us. That's especially the case in languages with undefined behavior, where we had this effect where correct optimization can change the behavior of an incorrect program. In other words, the bug only shows up when you turn on optimization. So that's one little caveat about why we care about this. Another question that we get, which is, I think, a reasonable question, is, well, there's this thing called dynamic deoptimization. In sort of modern language runtimes, you can attach a debugger late, and then it will only sort of disable optimizations at that point. That's really neat. It only lets us observe unoptimized execution. So, for example, with this game situation, it wouldn't help us, right? Because it's going to, when we attach the debugger, it will slow things down. And it doesn't give us the option of seeing the optimized execution. If that's what we really want to see, well, we can't, because the moment we attach the debugger, we're back into unoptimized land. So it's a nice solution, but it doesn't get us everything we want. OK, so here's a picture of dynamic deoptimization using the same notation we saw earlier, where we use the fact that there is a mapping, the language runtime, normally it's a JIT compiler, that knows the mapping from the object level state back to the source level state, or the unoptimized state. It does some on-stack replacements and very clever stuff to get there. And then we carry on in unoptimized land. The kind of compilers that Ryan and I have been worrying about are a bit less cooperative. They are not sort of tightly co-designed with the garbage collector and just-in-time compiler and debugger also all in one sort of thing. Instead, they're only caring about preserving the input and output behavior of the program. That's it. So we don't have nice properties about loopback edges, we have a safe point, or at call sites, we have a safe point. They only care to preserve the input and output behavior of the program. And that's your C and C++ compilers and so on. And what goes on there is not great, right? Because debugging is always lagging behind optimization. We're always getting optimizers that are breaking debugging information. And this is what happens if you search on the LLVM bug tracker. You find that there's a bunch of bugs where debug info has kind of got lost. Someone's made a new optimization. It's kind of messed with debugging. And eventually, some of these do get fixed. But in the meantime, there's been more optimizations going on, and more stuff has been broken. So debugging is always kind of lagging behind. So what are the other things that can go wrong with compilers like this? Well, it's generally not the case that we only have mappings in places where it can be a very precise mapping. Instead, you can always ask the debugger at any instruction, ask the debugger, oh, can you show me what are my local variables, what source location am I at, things like that. So, but because we can do it at any instruction, and the compiler has often sort of moved things around, or combined different operations together, often we get a sort of temporarily imprecise view. We're getting sort of seeing a bit of that old source level state, a bit of the new source level state. What we're seeing doesn't reflect any single state of a source level execution. If we were to just run the program under an operational semantics, we wouldn't actually see exactly the state that we see. We're seeing a kind of composite. That's one of the effects. Another effect is that stuff is just not there. It's like, oh, well, yeah, I can show you some of the variables right now, but not all of them. And that's the example that we started with, variable optimized out. So we can think about this mapping across a few dimensions. So this is just kind of summarizing what we've just seen. There's the density of the mapping, like how complete is it? Is it defined at all program points? Or maybe only a few? I didn't really cover semantic height. In fact, I meant to delete that one. But sometimes there are systems that will show you a sort of intermediate view that's not all the way back to source level, like some other notation. And then there's the question of, well, we have a mapping, but how faithful is it to what we would see in a source level execution? We've seen the temporal imprecision thing. We've seen the fact that some variables go missing. And sometimes it's just wrong, right? Sometimes the compiler will generate information that causes the debugger to show a spurious value, a spurious view of something. So our sort of underlying thesis is that a lot of this is down to how we approach developing compilers, right? And one of the things that compiler authors like to do is eliminate stuff. They say, let's eliminate this unused or redundant computation, which could be code, or unused or redundant state, like variables. And as we articulate in the paper much better than I can manage here, we should think about this. Someone needs to write a new textbook. We should think about this instead as residualizing, right? What do I mean by residualizing? Well, I mean anything the compiler wants to leave out of the object program, it should put in the debugging information. Debugging information is a computational peer of the object program. And that mess of printout that I showed you earlier embeds a Turing powerful stack machine, right? So it really can compute any function. So what should be happening is that as we make the program smaller, the debugging information gets bigger, right? Stuff that got eliminated from the object program by the compiler should be reflected in a larger, more complex debugging information embedded in the output program. Here's a little example of that. This one really does work currently in at least one compiler that I've tried. Okay, so this is some nonsense C code. Don't worry too much about it, but it's got a couple of loops, and the loops have an index variable I, and the compiler has added the blue code and deleted the red code, and you can see that the variable I has been completely eliminated. All the I's are crossed out in this example. So what it's done is said, well, we don't want to do array indexing every time around the loop because it's got a multiplication in it, that's slow. Let's just keep a pointer instead of an index variable, and we can increment the pointer all the way around the loop. It's classic strength reduction optimization. But it turns out our debugger can still print a value for I, even after this has happened. And the reason is that the debugging information says something like this. It says, well, all the other stuff is still in a register in this sort of fake example, but with variable I, well, it's gone away, but it has the value 0 over a particular range, lines 3 to 5, and it has a value given by this expression over the rest of the code, basically. It's, well, what's the expression? Well, it's like the new pointer that's been introduced minus the base pointer and then scaled down by the element size of the array. So it's where position we're working on in the array. And that means our debugger can still print out the variable I. That's what I mean by residualization, right? We've taken some logic from the program and we've put it into the debugging information. Now, compilers do this sometimes. They make a best effort when generating the debug info. And there's a sort of folklore belief that it's not possible to do a perfect job. And I'm in the paper, we're kind of arguing that that's actually wrong. And with the right kind of residualization, we can do a perfect job. And the first thing we're going to say is that part of the reason that compilers do a patchy job is that no one is holding them to account. There's no well-defined correctness criterion for the debugging information that they generate. We have a bit on that in the paper. We have some other work, both past and future papers about this. There's quite a lot in the paper. And the thing that people particularly mention is that, well, once we start moving code around, that's when things really break. I don't believe that for a second. In fact, I will strongly argue that this is not a showstopper that people say it is. But one little touchstone I want to raise is that it's already the case that hardware gets around this problem, right? We know that modern CPUs don't execute things just serially in the order that we give them. Here's a little snippet from a now very old but nice IEEE transactions on computing paper about way different ways to implement what are called precise interrupts in pipeline processors. And without getting too bogged down in the text, basically you keep a bunch of extra state around. So you have a bunch of registers that are what you're currently working on and a bunch of other registers that are sort of an older version that we can use. If we get an interrupt in the middle of something, we can roll things back. So this idea of keeping extra state seems really useful if we want to deal with some of the hairier things that are going on when we want to get a source level view of our optimized program. You could say they're keeping residual state. They somehow residualized the older versions that would otherwise be thrown away. So our game is that, well, we've got our functions. We've got our Turing powerful stack machine. So we've got Allen power. But what we don't have is the ability to travel in time. Patrick Troughton is definitely the best doctor, by the way. So if we can't travel in time, it means that we've got a problem when state is dropped by the executing program, by the optimized program. Because it might be, for example, that we have a dead local variable, dead from the compiler's point of view, but actually we might really want that at debug time. And so whenever we have something that is not computable as a function of the object program state, we currently have a problem. And we're going to need to residualize that state in order to solve that problem. Obviously, variables are one kind of state. There's also control state. If we start merging paths in our control flow graph, we've effectively lost some state. We don't know which one of those we're in if they're both sort of mashed together at runtime. So the root issue in loss of state is that we can't go back to the past and say to the world, hey, that input value that you gave me that I computed a load of stuff from ages ago, give it to me again, please. We can't do that. We're going to have to remember it as much as needed. Anything that we computed from that is fine because we've got our Turing power, but it's when we lose input values from the past that we have a problem. So the annoying thing about dwarf, so dwarf is the debugging information that I showed you the dump of near the beginning. there's a sort of tacit assumption in the design of Dwarf that there is no residual state. In other words, state lives only in the object program, which is annoying. On the other hand, there have been recent changes or additions to Dwarf that are tacitly contradicting that. These are better explained in the paper, but basically you can have one instruction where there's many source level views of that instruction, many source level states that can be constructed at a single program counter. And there's also some sort of magic operations that in your little stack machine programs you can say, oh, please get me the value that this thing had on entry to the call, without saying how you get it. Well, you get it somehow by keeping some residual state. Current implementations are not doing this, and neither of these mechanisms is at all general, right? So there's an open challenge to design a general state residualization mechanism for debugging. We know of one very nice approach that was in a thesis from only 25 years ago that is still not implemented in any widely used debugger that we know. But it's actually a very nice technique for remembering values as they're about to become dead as far as the register allocator is concerned, and then can remember them in the debugger rather than letting them escape from us. So why am I convinced that we can do a perfect job? And the answer is that there's a limit case to this idea of residualization, which is basically that you run both the unoptimized and optimized programs side by side, feeding them the same input. And we should be able to encode that unoptimized program in the debug information with the appropriate changes, rethinkings, whatever we need to do to make the debug information allow that. And then in the worst case, which would mostly not be realized, mostly we'd have more overlap between the optimized and unoptimized programs. But in the worst case, we can just have these two things running in parallel, obviously the unoptimized one running in the debugger and the optimized one running on the machine itself. There's a lot more in the paper. We have a correctness criterion that captures what should be true at debug time, even allowing some of this temporal imprecision. So we're sort of trying to be pragmatic there, but trying to also hold compiler developers to account by giving them a strong correctness criterion about local variables. We have sometimes people ask us about, is this all solved by verified compilation? The answer is no, and we explain that in the paper, and there's a lot more examples as well. So the punchline is that at the beginning of the talk, we were asking the wrong question because we used the singular. We were talking about the available debugging experience, but we should have said experiences, because we no longer have just a program. The moment we've asked our compiler to optimize the program for us, we have a family of program variants. And so if you just say, oh, I want the debugger to show me what's happening in the program, well, that's underspecified, right? It's an ill-posed request because there is no one answer to it. Nevertheless, if we can residualize both computation and state, then there is no limit to how complete and correct an illusion of source-level execution we can show, because we can conjure that up at runtime as needed. And the limit case that I mentioned is sort of the conceptual proof that this is possible. It would still require the user to say, which view do they want? Do I want to see the source level semantics? Then I'm not seeing the optimizations. Conversely, I might really care about the optimizations because I'm sort of doing some profiling that is sensitive to sort of caching, or so I might sometimes really want to observe at the optimized code level. But the user should be able to choose. That's all I've got to say. Thank you for listening. I'm happy to take questions.
Okay.
Check. Thanks for your talk. Sorry I missed the beginning. Maybe the question I have was already answered, but I was just thinking whether what you're doing could be applied to what would you call them? Are they embedded DSLs? DSLs that are translated to a source language. So when you're debugging them, what do you want to see? Do you want to see the DSL state or the state of the translated code? The translated code is not really what you'd like, but you need that to map back. Would that?
I think that's definitely, it's a requirement that fits in the space, and it's somehow, I don't remember how to slide around this. Do I have? I have 81 bonus slides, but none of them is the one I want. So I think if you have this explicit translation pipeline where you have many sort of representations of your source code, then it does make absolute sense to be able to see any of them at debug time. And that does fit here in the sense that if we can explain it in terms of the framework of mapping states, right? it's adding more requirements. So even with the sort of nasty C and C++ compilers I work with, there's some quick hacks that I've often thought about adding, which is, you could generate a line table for the before pre-processing code, is what you normally get, and a line table for the after pre-processing code, and you can kind of stuff them into the same binary and then make your debugger, allow your debugger to show you both. So it definitely fits into the space. I do think having that as a requirement makes things strictly harder, but maybe not much harder. So that's my best answer, I'm sorry.
Okay, cool. Nobody's behind me, so I'll ask another question, similar one. I guess you saw the talk on abstract debuggers?
Yes, really cool.
Yeah, but we have two kinds of different states. Do you think some of your ideas could apply in that context, or vice versa?
I mean, my gut says these are orthogonal requirements. I would love to have all the things at debug time. The thing is, we're really tied down by the fact that our constraint is that we have the heavily optimized code running, and that's like the bottom layer. And I don't know how to fit that into the model of the abstract debugging, but it's really worth thinking about, so thank you for asking.
Okay, thanks very much.
So Stephen, I couldn't help thinking when I saw your tenditious Doctor Who slide about, I mean, you're giving up on time travel here, but the people who are doing time travel with record, replay, debugging, it seems there's kind of a similarity, if you squint enough here, between what you're doing and what they're doing. So is there some crossover? Is there some way that you can use them or they can use you?
Yeah, so the crossover is this. They have all the past states, by definition, right? So when I told you my pedantic caveat would pay off, which is that, so they pay an upfront cost. They say, well, if you want to start your program, you've got to start it in this recording environment so that we capture all the input. And that means, yes, all the past state is available. We talk a lot to, we know the people at UndoDB and people at Panosco and Robert O'Callaghan's who maintains RR. And they still have the problem that building a good interface out of that is hard. And if your interface is saying you inspect one program state at a time, then if you want to see a past state, the Undo people said, oh, we just have to tell our customers to, if you can't see a variable here, step back a bit and maybe it'll become visible, right? So they have this nice resource, which is that they have captured all the past states. Whereas we're saying, what if I want to attach my debugger later and basically only start recording the minimal necessary stuff and as late as necessary. So we have given ourselves a harder problem in some sense, but there's definitely a big infrastructural overlap in terms of what we're building. What they're building is useful for us, and a lot of user interface stuff will be shared. And yeah, that's a bit vague, but yeah, big overlap, definitely. Yeah.
Do you have a question?
Yes, it actually relates to your question in a sense, because I was curious, because as I understand it, you're proposing that you keep residual state in the debugger. For example, these variables that become stale and no longer exist. And to me, that sounds like when you're running the program under the debugger needs to intervene at some points to collect this data.
Yep.
Do you have any idea about the cost of that? And can you afford that cost when you're running optimized builds in games, for example? I understand if you don't have the exact answer, but it's like, I'm curious.
Great question. So we mentioned that there's an existing implementation of this, and yeah, that one was really slow, but where did it go? There we go. So it's kind of unworkably slow if you use a conventional breakpoint in a conventional debugger, because that's doing traps. Traps are very expensive. There's, again, literature on doing really fast breakpoints by staying in process and, splicing a little trampoline and storing something so you could store something in a ring buffer, basically not slowing down the mainline execution very much. How much it slows down? Well, it depends on how many dead variables you have that you care about that you're doing this for. But basically, we don't yet have the data. This is not a results paper, but it's a great question, and it can certainly be made a lot faster than current implementations have managed. I would happily stake my reputation on that.
Yeah, but that's what you're saying with like injecting small trampolines that saves it sometimes only when the debugger is attached is a very cool idea for that, and it certainly saves you much.
Thanks.
Okay, having happily staked your reputation, we don't hear that one too often. Let's thank the speaker.
Thank you.
And we return at 4 o'clock for the last essay session. Thank you.
Hello, everybody. Yay, there's still people here. That's nice. Friday afternoon. It's more than 10 people. My bet was like, hopefully more than 10 people. So, Jonathan. It's not a paper, but it's an essay. Yes. Yeah, maybe close the door. Sometimes so. Thank you. So, welcome. This is the last session of Onward. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, more than 10. That's nice. So, there will be 2 more essay talks, and then we have a small conclusion. I also have slides for that. And for now, we have the linguistics of programming. Stage is yours.
All right, thank you. So, yeah, we're going to talk about some parallels between linguistics and programming, and of course this is not a new idea to connect these two, since language is right there in programming language and all, and people have written about this over the year, including a rather raucous dialogue at last year's Onward. But I'm going to try to do something a little bit different than most of the previous discussions I've seen, and instead of just sort of drawing philosophical parallels, I'm going to try to make the point that there are very concrete, specific things that we can take from linguistics and use to our own ends in ways that help us. And so if you think about, what do we do in programming languages and software engineering research? Well, we think about how software is constructed. We talk about the social side of that, the technical side of that. We think about how people use and produce code. We think about what properties a particular piece of code might have. Maybe it's buggy, maybe it's data race free, maybe it's both. We think about how code interacts with other things that exist in the world, like comments either in the code or in a bug tracker. We think about design documents. Natural language specifications is something many of us are working on now. We think about how people comprehend and understand code. We think about common properties that a programming language or group of programming languages either have or might have. And we think about what programs mean, right? And not just in terms of the computations that they express. And if you do a little search and replace here, you end up with a pretty reasonable approximation of what linguistics is about, right? They care about where language comes from, how it comes to be. They care about how people use and produce language. They care about properties of a particular utterance of some language, right? Are there pragmatic phenomena at play? Are there presuppositions? They care about how language interacts with other things, like when I point at myself or at you, and the context this matters in, because if I turn around and say you, I'm pointing at the wall instead of you, right? They care about how people understand language. They care about typological properties, properties that are common across many or all languages. And they care about what language means. What do these words that I'm saying right now mean to you, and how do you know what they mean, right? So if we take a very cursory overview of some major areas of linguistics, we can see a lot of familiar terms, right? Syntax. Programming languages have this, and it's not even Chomsky's fault. Semantics. Hey, our programs mean something too. Pragmatics, right? We maybe don't pay enough attention to this question of why did I write this code instead of that code? What's implicit in this code but still supposed to be obvious somehow? There's aspects of morphology, right? James and Robert made this nice point about pass by reference having a bit of a flavor of being an accusative case. There's psycholinguistics and neurolinguistics, right? We have people who stick people in fMRI machines like Janice Sigmund and collaborators and see what happens in their brain when they're understanding a piece of code, right? And there's even orthography, writing systems. Anybody ever dabble in APL? Couple people, yeah. Unicode in your code, yes, yeah. So we'll come back to that, because that actually, even though it seems a little superficial, it comes back and we'll talk about it later. So there are some deep commonalities here, right? So PL and SE and linguistics, we all kind of care about what things mean, different things, and how they're used. And we generally are looking for explanations. Why do they work this way? How do they work? And we largely spend a lot of time staring at linearizations of highly complex structures with non-trivial, context-dependent, and often socially constructed interpretations, right? And we care about how people use either code or language to communicate with multiple audiences. And for code, this is not just our compiler, but also our future selves and our peers who are supposed to understand something about what we did, right? It's not just for other researchers that we want to prove how smart we are, right? So there's enough similarities here between linguistics and our fields that there are a lot of ideas and tools that I would argue not only can, but should inform PL and SE research. And I think if we don't take advantage of that, we're doing ourselves a disservice. Before I get into details of like concrete things we can look at transferring across these boundaries, I want to fix a common misconception that I run into very often, which is that linguistics and computational linguistics and NLP are not the same thing. They are three closely related areas, but they're looking at very different problems, right? So most of us here are in computer science or software engineering departments. A fair number of us are doing software development in industry. And so it's very easy to get this impression that like, hey, you know, these things that happen with neural networks and all that, that's linguistics or computational linguistics. But most linguistics isn't even computational because it's about how people use language, right? And in particular, most linguistics has absolutely nothing to do with LLMs, right? So people do experiments from time to time to say, can we use an LLM to simulate what a person might do in this kind of situation? And with a couple exceptions, the answer is basically no. They don't work the same way as humans do, right? So we're not going to say anything more about them today. Everybody here already knows what they are. So we're going to talk about other things that you might not be aware of. And just for context here, we're not going to talk about everything in the essay because we don't have time. But even the essay is only scratching the surface, even though there's 191 references, right? The only thing I've written that has more references than that was my dissertation, right? So even though there's that much there, we're still only scratching the surface, right? So there's way more than what I'm going to say today. As far as what I am going to say today, we're going to kind of take a tour of a few different levels of possible interaction, from some higher level, how do people interact with some of the things we might say or do or try to say or do. We're going to talk about some ways of looking at data that comes out of developer processes that we could probably profitably go rating the linguistics literature for. And we're even going to talk about low-level sort of fiddly things about what can I do to make my compiler more interesting or flexible or have other advantages there. So there's stuff at all different layers, all different flavors of TL and SE research. So we're going to spend a fair amount of time talking about pragmatics. So pragmatics is the study of intended but unstated meaning. These are things that we are meaning to communicate, but we're not explicitly saying, right? So like a conversational implicature is, if someone asks me, did you get that code working? And I said, oh, I spent last week in debugging hell. I'm kind of leaving it implicit, but you would gather that I didn't get the code working, right? But it's only implicit because if I had kept going and said, but I got it working in the end, it would have been different, right? So there is somehow this implicit communication. There's this notion of deixis, right? Different parts of text can refer to other parts of text. And we do this all the time when we write code comments. The loop below and the loop above, right? If you move the context of that comment, it doesn't mean the same thing anymore. Or presupposition, right? This is a method that is called when the foo component does X, Y, Z. Well, this only makes sense if there actually is a foo component, and there's still a foo component, nobody deleted it, and somebody actually calls the foo component, and that it does the other things that we talk about in this comment. And if any of that changes, then the meaning of this thing changes as well. Or scalar implicature, right? If I say that this library is acceptable for our purpose, well, why didn't I just say good? If I didn't say good, it's probably because I don't think it's good. I think it's only acceptable, right? And so this turns out to have a bunch of implications for how people interact with text that we might give them. So here's an example that might be relevant to those of us who do user studies about, say, formal methods kinds of things. So there's this thing called a Hereford disjunction, where you're asking people A or B, but it's a little bit weird because one of them implies the other. And so if you ask people if A or B is true, they will read this normally as being like a little bit off. And so they'll try to fill in, like enrich this so that it makes more sense that you're asking them a contrasting question between these possibilities. So here's a sort of a PLSE analog of a famous behavioral economics example. Some researchers asked a bunch of people, given that Aaron likes Python decorators, is it more likely that Aaron is a Python programmer or a programmer? And now most of us would see this and say, like, okay, well, this is in contrast, like an either or. So they probably mean like Python programmer or a non-Python programmer. But they like decorators, they know about decorators, so they're probably a Python programmer, right? Except that's not actually what the people who designed the original experiment meant. They meant the equivalent of, is the probability that Aaron is a Python programmer greater than the probability that Aaron is a programmer? And the answer is, of course, no, right? But this is not the way most people interpret this question because the disjunction is a little bit funny, right? So this is kind of a roundabout way of saying that a lot of us are increasingly, and this is good, starting to do more human evaluations. We're asking people these questions, but there's really subtle phenomena that it would behoove us to know about as we're designing these things and be aware of, that we can ask questions that don't go across to other people the same way we mean them. And this is especially true for logical words, or and similar logic-related terms. Turns out they're the source of triggers for a lot of these kinds of extra enrichments. So one of the really classic examples here is conjunction buttressing, right? So further supporting structure around a conjunction. And the classic examples from linguistics are things like, I took out my keys and opened the door. And this is usually interpreted as, I did these things in that order. I first took out my keys, and then I opened the door, probably using the keys, right? And as opposed to being sort of simultaneous, right? Or even happening in the other order, like I opened the door and then went inside and took out my keys. Or I got on my horse and rode off into the sunset, right? There's a strong implicature here, it's not explicit, that probably you first got on the horse and then rode off into the sunset, instead of, you know, riding off into the sunset on a dune buggy, getting home, and then getting on your horse, right? But these are things that are implicitly understood when we speak this way in English, and similar phenomena occur in most other languages. There's also, if I'm going to blend the boundary between pragmatics and semantics a little bit, this notion of a thing called a habitual sentence. So it's a sentence that is implicitly expressing a recurring state of affairs. Like if I say, I read the archive mailing with my coffee in the morning, I'm not explicitly saying this always happens or that this happens daily, but this is the intended reading, and this is what most people understand if you say something like this. So what does this have to do with us? Well, so Ben Greenman and some other folks wrote this really nice paper last year where they looked at what mistakes people make translating English into linear temporal logic. And if you look at the data, which is what I've spent the last few months doing since I wrote this essay, it looks like there are some mistakes that are tied to these pragmatic phenomena, right? So one of the common things that happens is people leave off a next operator in temporal logic, which says this part of the formula happens later than what we're looking at right now. And this often happens right after a conjunction. So if you were to try to translate, I took out my keys and opened the door, the way we typically understand it, you would say, I took out my keys and eventually, later, I took out, or I opened the door. And people leave this off. So this seems like an interesting parallel here. And there's also this question of people leave off a top-level always operator that explicitly says this always happens. And that also corresponds to the difference between interpreting this habitual sentence as the recurring state of affairs versus just something that happened once. So let's keep going. Let's think about some other areas of linguistics and what they might have to teach us. So let's talk about language acquisition. So linguists, no surprise, have spent decades studying how people learn languages. And in particular, they've even broken it out into interesting differences between, obviously, the first and second language have some differences, right? Because the second time around, we've already got a language to start with. But even learning the third language turns out to be different from learning the second in interesting ways. And there's a little bit of evidence that even going to the fourth language introduces some new stuff to the mix, right? And they've done a lot of experiments studying cross-language ordering and how that affects outcomes, right? So someone who's a native English speaker learning French is going to end up with their knowledge of French in a different state than someone who starts out from German and learns French. And if we start learning more languages, well, if you learn English and then German and then French, you're going to end up with French in a different state than someone who starts with German and then learns English and then learns French. Even though you're learning the same set of languages, the order turns into yielding different results, different kinds of mistakes, right? There's studies of typological differences and how that affects learning. If you're learning a language that's sort of in the same language family as something you already know, this makes certain things easier and certain things harder. And this should be familiar to anyone in this room who said something like, if you learn one functional programming language, you can learn another one more easily, right? That is, in fact, exactly that kind of argument. And they've done studies of intermediate stages of progression in learning their second or third language. There's interesting phases to call out: the early phase, where they're really still figuring things out, and then progressively later phases. And so we study how people learn programming languages too, but these are not experimental setups that we've done, as far as I can tell, and I've looked. Not to say that it's totally trivial, because there are some differences, of course, between natural languages and programming languages. How many of us speak at least 5 natural languages? Yep, that's what I figured. How many of us can productively write in 5 programming languages? Most of us, right? So there is, we dabble more in programming languages than we do in natural languages, right? So that does complicate, finding people to even do these kinds of setups. But let's take this seriously, right? So let's assume that natural language acquisition and programming language acquisition should more or less be pretty similar, right? Maybe there are some differences, but let's assume that they're pretty similar. So let's take that perspective and let's look at a language acquisition study that we've already done and see how that lines up with what the natural language acquisition literature would say. So let's look at what was at the time a little bit of a controversial paper. Yes, exactly. So Stefan Hannenberg wrote this paper in 2010, where basically he asked a bunch of students who had just taken intro programming to learn either a typed language or an untyped language. And they're the same object calculus, but either a typed or untyped version. They got an IDE. I'm pretty sure they got a debugger, right? So pretty comparable experimental setups, other than type checked statically or dynamically, and asked them to implement a parser. So what happened? Well, the two groups had basically the same rate of bugs, right? Basically the same rate of bugs, same kind of bugs. But the typed group took longer to get something running, right? Not necessarily to get something fixed, but longer to get to the point where they could even run test cases. And so this was interpreted as type systems failing to show benefits. And of course, it made lots of us who work on type systems very sad, because we felt misunderstood and misrepresented, and there was all sorts of discussion at the time about this. But let's take a step back and let's say, what would the natural language acquisition literature tell us to expect here? So in that context, this is actually exactly what we would expect. The early stage of learning a new language, when you already know some, and this is true for L2, L3, and so on, the initial mental model for the new language you're learning is going to be a garbled version of a language you know, right? This is why, when I was first learning German, right, one of the things English speakers struggle with in German is word order. Where does the verb go in the sentence, right? Because in English, we stack them all together at the front, as in many other languages, and in German, if you have more than one, something gets jettisoned to the end of the clause or the end of the sentence. So what this means is basically, in this context, all of these participants still basically had a mental model that was Java, right? They had a short tutorial, but that's not enough to majorly change someone's mental model of what an object-oriented program does. Now, you're probably saying like, okay, yes, I mean, they're both object-oriented languages, and that's fine. What does this have to do with the typed versus untyped distinction? Well, type checking at the level you see in CS1 Java is a grammatical property, right? It's grammatical agreement between this part of the program over here and this part of the program over here, needing to be consistent with each other. That is a context-sensitive language recognition problem, and many natural languages are mildly context-sensitive, right? So this agreement actually is a grammatical property in how people think about relating distant parts of some sentence, which means, in a very literal way, the untyped group is effectively trying to write typed code just without the aid of a type checker. So this is not a group of people who are going to instantly switch to taking advantage of whatever flexibility or liberties dynamic type checking might allow. They're mentally really trying to get these different pieces to agree. But only the typed group was actually slowed down. Only the typed group has somebody stopping, and every time they made a mistake saying, hey, wait, I think you actually meant Dame instead of Dane, right? Or something similar to that, right? So you might learn better in that way, but it would take you longer to get your point across, which is what happened here, right? So I want to emphasize, I'm not trying to knock this study. I think this was still a study very much worth doing because it shows, hey, here's a concrete example of natural language acquisition and PL acquisition behaving equivalently, behaving similar ways, right? So that maybe is not the intended original purpose of the study, but this is what I get out of it now, and I think that's really cool. The essay talks about a second example, looking at another somewhat contentious paper on the intuitiveness of programming language syntax, right? And so in that paper, one of the things that they found was, if all the keywords are English keywords, then great, people find this more intuitive, and you know why. I think the best example for this is actually an anecdote from Felina's splashy Onward keynote last year, where she told this story of a student learning Python, got an error message, they read it aloud to the instructor, and what happened was they read part of the message, then paused, and then continued onward like they had maybe skipped a word or something. And it was a comma that they had skipped, because punctuation in natural language is not meaning-bearing. So moving to a setting where those characters do bear meaning is a significant change, right? And this is parallels to people learning language with a new script, right? Also, I didn't know this at the time I wrote the essay because it was, of course, only out later, but there was this very cool splashy paper yesterday where they took natural language teaching pedagogy and applied it to teaching of programming languages and got some really cool results. So you should totally check that out. All right, so on from language acquisition. Let's talk about looking at traces of conversations from software contexts. Right? So the past 15 years or so, software engineering folks have really spent a fair amount of time looking at developer mailing lists, discussions on bug trackers, discussions in Slack about what was happening with their software. Turns out this is something linguists have looked at for a lot longer than software engineering people. Right? So there's this large area called discourse analysis in linguistics. And it's the study of how longer linguistic utterances acquire their meaning, with a particular emphasis on discussions, interactions, and exchanges between different groups of people. And this is something that linguists have been studying in earnest since the 50s, and if you go a little bit further for the early signs, they go back to the 20s. So they've been at this for a long time. And this deals with questions that the software engineering folks are now reckoning with in the software engineering context, right? What is the relationship between this text, the context in which the discussion is occurring, the power differential between people involved, how much people can remember, these sorts of things. And this is really exactly the sort of thing people in SE are now starting to look at. I shouldn't say now starting. They've been doing this for a good bit over a decade now. But they are really looking at this in developer chats, issue tracker chats, mailing lists, and these other sources where developers discuss what happens with their software. And that particular context is called computer-mediated communication in some areas of linguistics. And they've been looking at that since the early 90s. And they have rich studies now for how things like gender or race, sexuality, power positions in a project, how those factors affect how people participate in these discussions. And so these are specific topics that are now showing up in research in software engineering. And I have a hard time thinking that there's nothing to learn from this larger body of work that's a little bit older. All right, so I did promise that I would have something to say about stuff that's not people, right? Because many of us implement compilers and runtime systems, and so we're interested in these little fiddly bits. So here's just one taste of something. So linguists, of course, spend a lot of time dealing with grammars, right? They deal with syntax, one of the major research areas in linguistics. So there's this thing called a lexicalized grammar, which is a style of grammar where instead of recursively specifying a bunch of fixed set of categories, right, the non-terminals in your context-free grammar, you have a few base things like noun phrases, articles, adjectives. But anything more complicated than that, actually you give just a description for how each word combines with neighboring words. So you could switch between prefix and postfix and infix choices for plus, for example, just by giving slightly different grammatical types to the plus operator, right? So in this notation, the slashes lean in the direction of the argument. So prefix is going to look to the right for its first argument, and after it gets that, it's going to look to its right for a second argument. Postfix is the reverse, and this infix, this one happens to look left first and then right. If we're reading outside in. And the advantage here is that you can add or remove or swap individual entries or their grammatical types as needed. And since you don't need to go out of your way to specify a lot of the sort of intermediate categories in your grammar, if you want something that's conceptually like a wildly new category in your grammar, you just build it up from these almost function types in the grammatical types. And you don't have to then add some new non-terminal and plummet through the rest of your grammar. You just say how it interacts with things that are adjacent to it. And this is very modular in a nice way that has some tie-ins to language levels or internationalization or just experiments with your syntax, right? And there's very general, nice parsing theory there as well. And if you're wondering, okay, well, if we got rid of my context-free grammar, where'd my parse tree go? Well, there's an interface between these things and semantics. And guess what? When linguists do formal semantics, they use lambda calculus, right? Which we're all familiar with. So you can abuse that to get ASTs. So you can say the semantics of plus is going to bind its left argument and then its right argument and give us a plus node, right, with things in the right place. Just as a small, sort of simple example, right? And so wrapping up, there is way more for us to learn from linguistics that is directly applicable to all sorts of things that many of us are doing. We study things that have very strong similarities or analogs to things that linguists have been studying, in some cases for longer than we've been studying them. There are results in linguistics that seem to have direct application to things that we are doing on a day-to-day basis. I showed you a couple examples, well, showed you one and hinted at a couple more where if you assume natural languages and programming languages are similar enough, natural language acquisition research predicts what happens when you do PL acquisition studies. And that linguists face a lot of the same sort of tooling and abstraction and modeling challenges that we do, and they've kind of been doing their own thing for the last several decades, and so they have like a very different suite of tools and techniques and ways of looking at things that I think are, at a minimum, very interesting, and I think more probably actually directly useful to us. So please, 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 if you're doing, I don't know, anything in software engineering and programming languages, go learn some linguistics. Minimum, the worst case that happens is you learn a bunch of really cool stuff. And probably you'll come up with at least some new tool or technique or some new way of looking at your problems that maybe you wouldn't have come up with on your own. Right? Thanks.
Thanks for the talk. We have time for questions.
Hi.
Hi.
I actually did study linguistics
Yes,
40 years ago. And so I was fascinated by your talk and what you do. I mean, there already is actually a lot of overlap with linguistics, not just subject matter, but the origins of a lot of our techniques in terms of parsing, phrase structure grammars, lexicography, and whatnot. Actually, right, BNF comes from Chomsky normal form.
Absolutely.
What we haven't done is the softer side of it.
Yes.
So the fact that you mostly talked about the interaction with people, I like that because I was fascinated by psycholinguistics. But one of the things you just went over very quickly was semantics, which is sort of there in between the pragmatics and the syntax. One of the things that I've seen over the years is that when we talk about semantics these days, it's like ontology and the semantic web, which when you look at it, it's just syntax.
Yes.
It's an encoding of our semantics.
Yes.
And you talked about formal linguists mapping to lambda calculus. Well, kinda, except that's really just mapping to another language, right?
Yes.
The really interesting study is what do languages mean? What do we mean by utterances relative to the real world?
Yes.
When we start talking about programming languages, and especially what I'm interested in is modeling languages and the real meaning of ontologies, that's that mapping. And that, to me, is one of the really interesting things from linguistics, which isn't solved in natural language studies either. But I think we could contribute back and forth on that.
So you're right. Like the connections to what linguists call semantics, and I do mean linguists, not this ontology stuff that NLP people do.
Right.
Right. I didn't talk about that much because I would just be kind of waving my hands and talking about another slightly different variation of lambda calculus. And so I thought it was probably a better use of time to focus on, like you said, the people side of things. But yes, there's a huge literature there, including human studies of how do you figure out what an individual word means in different contexts.
Right. Well, I mean, that was some of the earliest linguists, were looking at individual words before Chomsky in the 19th century.
And it's still alive and well. Actually, I wrote the author response to the reviews for this essay sitting at Experiments in Linguistic Meaning, which is a new conference that is held at Penn every year.
Yeah.
They're still hard at work and doing really cool stuff.
But I mean, back in the day, Montague grammars were basically denotational semantics for natural language.
Yep.
But again, that sort of begs the question of, is the world really represented by lambda calculus or by mathematics? What the meaning of a word isn't the lambda calculus, it's how we relate to the world. And our programming has an operational side, which lets us operationalize some of the semantics, which I think actually makes it interesting in terms of language. Can we think of language also in an operational way, semantically, natural language?
We have more questions. Thank you for the comment.
Hi, thank you very much. That was really good, really great. I really like to see these links being made. I think it's very exciting. I wanted to ask what your view is on some of the differences, because I know there's obviously lots of similarities, but that there are also differences. Linguistics, although there's formalizations, it's getting at something that's a bit more fuzzy, a bit more hard to pin down.
And this kind of echoes what you were asking about a second ago as well.
Yeah.
And it's true. And so in some ways, and so I spent the last couple of years using actually categorical grammars and those kinds of formal semantics to bind natural language to formal specifications. And in that work, I talk about how actually our lives are easier than linguists because we're talking about this program right here, right? Like it's right there. Yeah. We know what the semantics of the program are. We're not trying to figure out what is a cow? Right? Which linguists are genuinely trying to do because it's kind of like an amorphous, fuzzy concept, right? When does it count as a cow and when does it cross over into being a dog and these sorts of things.
Right. Thank you. Thanks.
Hi, thank you so much for this talk. It was really interesting to see these comparisons between linguistics in the natural sense and in the programming sense. I've been interested in parsing for a while and kind of both sides of it and whatnot. Earlier in the talk you asked how many people here can produce in 5 different natural languages, and I don't know if anybody raised their hand, but very few. And then you asked how many people can produce in 5 programming languages, and I think most people here did, because yeah, most people can probably, at a programming conference, can probably produce in 5 languages. So my question is, well, what do you think of like what it means to have fluency or some level of like partial fluency or productiveness in a natural language versus a programming language? Because I think there's like a reason that I don't know 5 natural languages, and but I can like work in 5 programming languages.
I mean, you did pick up on something that was intentionally a little bit of a rhetorical sleight of hand to kind of get the reaction I wanted, where I asked about fluency in the natural languages and competence in the programming languages. But even in linguistics, this notion of fluency is not like a hard and fast thing. And even though, like, you know, for decades, the baseline was, you know, comparing people's language skills against an L1 native speaker. And in recent years, people are actually starting to question even that, if that's really the right baseline or if the baseline should be slightly different. And so that's something people are actively kind of debating. So I don't know what counts as fluent in certainly a programming language.
All right, thank you so much, appreciate it.
There's still time, there's more questions.
Hi, thank you for the thought-provoking talk. I wanted to discuss the Java language transfer experiment that you discussed. Couldn't you make the opposite hypothesis based on the language learning, that like Java is a strongly typed object-oriented language? My hypothesis would be that, you know, people learning a second language would do better with another strongly typed object-oriented language.
You could certainly form that hypothesis, and there's stuff in the linguistics literature to support that as a baseline expectation. Although I will emphasize that that's never the only difference, really, between especially natural languages. So it's always in the mix with a bunch of other confounding factors. But there's some stuff to support that as well.
Okay, I guess I'm asking, why did you form your hypothesis as opposed to the opposite one? Like the claim is that the linguistics research would support.
Oh, I see.
You see what I mean?
I see. So the question is, what counts as better, right? And the issue is, what was measured in that experiment was how long it took them to get something working when they either did or did not have something interrupting them, correcting their grammatical mistakes constantly. And so, you know, when you're talking about like they would do better with types, well, you could make that argument longer term, that they would maybe reach competence or fluency faster, but the initial stages are going to still be the same. The initial stages are, you know, it's not exactly the same as Java. I'm going to make mistakes, right? And this is why the knowledge about like the different stages of learning a new language matter, right? And so that's how I ended up with this hypothesis instead of
So
that,
then,
which was maybe valid for like a longer term.
So, Jonathan? No? I have a quick question.
Sure.
Just unlearning came to my mind.
Unlearning.
Overriding concepts, like, have you stumbled upon anything like in that, like, can I remap the string concept in a new language?
Remap the string
right,
concept in a
whatever
new
word
language.
you know, node, or some operation,
like you
some
mean
operation.
learning the new words in a new language.
And the difficulty of remapping concepts when learning new languages.
So that's not something I spent a lot of time on, but actually that splashy paper from yesterday that I cited does, at least touches on that. So check that out, and they've got lots of references.
Let's thank the speaker again. So we should have closed the doors. Let's come to our final essay. The hidden program state hurts everyone. Stage is yours.
Thank you. I'm just going to put on a timer for myself. So, hello, my name is Sverre Þorkesson, and I am a PhD student from ETH Zurich, Switzerland. And I'm here to present this essay that we call "The Hidden Program State Hurts Everyone." So, first off, before I go into the main point that we have in our essay, I just want to show you some pictures of non-software developers working with computers. So in this case, we have an air traffic controller who is looking at radar and communications information on a computer. We have a meteorologist analyzing weather data, a physician looking at patient data, and finally a seismologist working with earthquake data. So, of course, this looks pretty weird because this is not how these photos actually looked like when I found them. So this is what it actually looks like when people work with these technologies, at least according to the news reports where I found these images. So my question is, if this is how it works for so many different professionals, not limited to just these four professions, why is it that software developers work so extremely differently? So, in contrast to how they do it and how we do it, we work with static representations of text, kind of like this, while they work with dynamic representations. And it's not like that we are able to take a look at this and understand immediately what this means. We construct our own mental representations of the code to understand the state of the thing that we're trying to model or to comprehend. So in many cases, we think that these textual representations just add a layer of complexity to the way we do things. So when I was preparing these slides, I was asked by one of my colleagues, well, why do you have to make it a guy from the Matrix? Like, this looks just really cool. Like, I want to be this guy. Like, these movies are impressive. Like, we think it's cool because, I mean, we don't understand what's going on. We see like these, kind of like what Feline was talking about in her presentation on Wednesday. Like, we think that when something is difficult, when something is totally incomprehensible, that means, wow, this is something I want to do. Like, this is something I want to aim for. This is something I want to make a career out of. When things are easy, like if if the Matrix was built in scratch or a block-based language, I don't think this would ever have been popular. Like, there would not have been any sequels. So, and this leads me to the next question, like, why does this even matter? Like, if computer programmers are so happy with the tools that we have, well, does it impact them negatively? And we think it does. Like, we think that these complex representations that software developers work with, that they harm their performance. And to moderate this belief, I would like to take an example from chess. So I have this book that I got when I was a child called Across the Board with examples of chessboard problems. This is not quite the same as chess problems. These are problems that are based on maybe simpler representations of chessboards with different types of pieces. So this here is the oldest chessboard puzzle in the world. And the goal is to find a sequence of legal moves for the knights so that they swap positions. So this is something that is relatively difficult to do, not particularly challenging. So for those who are not familiar with chess, a legal move on this 3x3 board would be that the knight could move to non-adjacent square of the opposite color. So we could, if we are allowed to see the state, and if we are allowed to manipulate the knights, we can find a solution after some trial and error eventually, like kind of like what you're doing here. This is a very nice way to actually work with the problem. It's called direct manipulation. But if we were a computer programmer, this is more like how we would do it. And this is just a terrible way to do things. You see, we don't see how the state updates after every sequence of moves that we have made. Like, it takes a while, we can make errors, and like it won't run. And we have a hard time understanding like what the error messages even mean. So I think that this example is a very good illustration of the problem that we are experiencing, and like how much nicer it is to have an ever visible program state for whatever task we are doing. And moreover, the point of this particular example is that not only does the state representation matter a lot, but that we also have a good state representation. So you may have noticed that, like, for this Jesper problem, the legal movements for the knights can be modeled as a graph, like you can see here on the left, which can be untangled to give a better state representation. So when you do it like this, the problem is a lot easier to solve. So on the left, it's trivial to see like how we can actually swap the positions of the knights. So you see like what we're doing on the left has a matching move on a state representation of the right. So this is very easy. So I want to take this further and try to understand better what examples like these ones and others can tell us about how we should design good programming environments. And what serious or professional chess players like to do, in addition to playing games, is to analyze their games, and they use software to try to do that. They have engine evaluations telling them how they could have played better, and like they try to look at games and understand how their opponents have played in the past to get a feeling of what they might encounter in their actual games. So a system like this looks in many ways similar to an IDE for a computer programmer, but maybe the biggest exception is that we have this state representation of the problem that we're trying to solve on the left side. And that comes with some useful features like some visual scaffolding. We can see like what was the last move that the player made. We can see visually what would be the suggested move from a computer in a position. We see like a history of the moves that have been played in a game so far, and we can explore variants that we can easily step into and expand and collapse. We can see a history of games that have reached this position and the success rate that players have experienced in these particular games, and so forth. This is also similar to how professional creatives work with image editing. We have like a state representation of the image that we're trying to build. We have here on the left, we have like clickable actions that we can use to manipulate the state, and we can see this when we use it. We can see how it affects the state immediately. We don't need to like write this and wait for it to compile. We can skip this edit compile cycle altogether. And what I have been trying to build together with my collaborators at ETH over the course of my PhD is a language for programming that resembles this in some ways. So here at Onward and 22, I was here with my talented collaborator, Gio Waitman, who we submitted a paper on this programming language Alcott that has some resemblance to like this chess software that I was showing you and the GIMP image editor that I was showing you before. So we have the program state, which is always visible here in the center of the screen. We have a list of actions that we can use to change certain features of the state, and we will see how this affects it immediately. And we can use this program state to create functions. We can do programming on this. We can do quite a lot with it, actually. Like, I'm going to show you a video of how a recent version of the system could be used to create a function that computes the dot product of two linked lists. So right now here we see that I have created a function which we call dot product, which takes 3 input nodes, which will be used when you call a function in the future. These are the nodes A, B, and C. We define some example values for these nodes. So we can see when we do actions on the inputs, how their values change. Not so that these examples have to be the values of the input, but just so that we can get a better feeling for how the things that we're doing affect the program as we are writing it in a live way. So here we create another temporary function called addProduct, which we can use for the function, which will take 3 inputs, take the product of the first 2 nodes, add it to the third input node. We create some example values. We create a temporary new node to store the product of A and B, just like this. You see 2 times 3 is 6, so these example values are helpful to tell us that we actually succeeded in what we are trying to do. We add this value to the node that had the value 1, so 1 plus 6 is 7. We can use the program editor to see, like, to step through this function. This is a new feature. And then we can use this helper function here in this dot product operation. So you see now the value is 8, and we call the function that we're defining recursively, again, on the child nodes of A and B. And this is all we needed to do to create a dot product that works on 2 linked lists and the third input, C. So if we then try calling this on some alternative versions of the input, we can step through and make sure that the program actually worked. So, and we can step into like the function calls. We can see that this works in a general case. So we create 3 new nodes. As you see, Alcott is entirely graph-based. The program state is just going to be one big graph. We create some example values. And call a function we just defined on the parents 3 and 1 and the node 0. And we should see the value 3 plus 2 times 6, 15. So we know that this works. So we did all of this without writing any code. And more importantly, we were able to see how the program state changed throughout the entire, not execution of the program, but through the definition of it, which I think matches nicely with how we can do other types of creative work, like I was showing you before. So some changes that we have made since we presented this paper in 2022 is that now we have a proper program editor, which is what you see here on the right, that we can actually use to step through the program. We have support for example-based programming that allows us to see on a more granular level, like how the input is changing throughout the definition. We have support for custom queries. We can do branching like we did before, but in a more detailed level than we made possible. And we have made some simplifications that mean that we no longer have like a clear distinction between the parts of the system when you are defining an input to a function, when you are asking questions about it, and when you're doing actions like calling existing operations, which seems to work rather nicely, at least for the context where I tried this. So far, where we have been experimenting with this is in computer science education. So this is where it seems to be most effective. And the reason, or well, there are many reasons why we have worked with education as a starting point. One point is that this allows us to gradually build the features of the system, that we can start with more simple things that are nevertheless important to students to learn. It's also something we wish to do because I think computer science education is very important, and that more computer scientists should care about it. And also because of these attitudes that we were talking about, that I was talking about in the beginning of this talk, that I think that many developers don't necessarily see the value in working with a system that radically changes how they do computer programming in a way maybe that can sometimes devalue their expertise or make it more accessible to others, which is not necessarily what people always want. So this way we can try to not only present a tool that is effective for hopefully a lot of people, but that we can also change the attitudes that go along with it. So another question that I get frequently when I show this tool to people is, why do we need something like this? Why aren't the existing tools that we see so many papers right now on in CS education venues, why aren't they sufficient? And this is just because of the problem that I was talking about earlier. We think that, for example, block-based programming does nothing to address the opaqueness of code, and neither do large language models. So I want to show you that, and I think this is very important, to validate whether this actually works. We do a lot of user studies, and this is something that is appreciated in CS education venues, and I would definitely like to see more of in general when it comes to new technologies. We do user studies with students of every age group. We did, for example, a study on secondary school students with an average age of 14, where we showed them algod, and we asked them to compute some recursion-based tasks, like, for example, to take a tree input and to compute what would be the depth of every node in a tree. And then we gave them a similar environment in Scratch with the same tasks using the so-called make a block feature that also supports recursion for Scratch. And then we gave them a post-test, which was based on a validated instrument for measuring understanding of recursion, the basic recursion constant inventory. And we saw that in this measurement that students both performed a lot better when they were working with our system algod, which we attribute to them being able to work directly and see the program state at all times. And also they performed a lot, they had a lot higher learning outcomes, probably partially due to chance, but nevertheless this is a consistent trend that we see. So Cohen's d, that means the difference between the two means of the populations that we tested divided by the pooled standard deviation. So, and we did another study with undergraduates when we compared algod against Python, this time with simple programs that did not require recursion. We measured their cognitive load. We used eye tracking and galvanic skin response to understand if they thought the tasks were challenging, and surveys on top of that to see like which self-reported cognitive load levels students were reporting. And again, we saw much stronger performance in algod and a lower cognitive load level also in our system. We did a study on program comprehension when we showed students existing programs in Python and algod and measured their performance on some questions that we asked them about the programs, like to measure how well they understood conceptually and mechanically what the programs were supposed to do. Again, seeing a strong performance improvement and a slightly, but not very meaningfully, higher enjoyment. And lastly, this was a study I just presented now in August. I did another study with undergraduates where we actually measured their cognitive load with an EEG, like these headsets that you can see here in this small image on the right side, to measure, to get a more objective understanding of the cognitive load levels. We can, it's possible, according to the literature, to convert the surface level electricity levels from the scalp into different frequency bands that whose strength corresponds to different levels of cognitive load according to some of the bands. So we looked at the theta and alpha bands coming from this equipment to understand if their cognitive load level was different. And this time we used more complex tasks. We used trees and linked lists. And again, the control environment Python to see how students compared. Again, seeing a strong performance improvement, but this time not a meaningful difference in cognitive load, according to neither the EEG equipment or the surveys. But for all of the studies, we are comparing our language against something that students are already familiar with, both Python and Scratch, further strengthening the results. So I think we see a rather consistent picture when seeing if this language actually is effective. So what we see here is that for students, for CS education, this seems to work, at least in the context of the studies that we tested. I don't think this is has to be like the ultimate solution to how students learn programming, but I think it is at least a good start, and it validates some of the thinking that we have been having about how we can make more effective programming environments. But what we have been thinking also about over the last years is this something that we can actually extend beyond CS education? Is this something that can actually work for professional developers? And we are at least hoping that this can eventually reach that level. One question that you might ask when you see how Alcott works, like in the example I showed you, is how does this work when we have an enormous program state? Typically, we're not trying to do such simple activities like trying to compute the dot product of two lists. We are maybe working with billions of variables or data sets that contains, or spreadsheets that contains millions of lines. And the system that I showed you is doesn't work in the current form to deal with something like that. But an idea that we have is that we can hopefully try to abstract this a little bit so that nodes can represent a more complex structure, which can in turn contain elements that contain a more complex structure in turn. Something like this, so that we could have a node that represents, for example, a list of guests, and so that each guest represents some more complex structure, like what we see here on the right. And another question that we get when we talk about how we could try to extend Alcott to work for professionals is, well, since Alcott is graph-based, how would this work for some different types of data? Like, can this actually, is it scalable for some existing data that takes some other forms, like tables, for example? And my opinion is that, well, maybe not. Maybe Alcott is, it's possible that this is not going to be the best tool for the job, but we my opinion is still that the computational paradigm that I was showing, and like this idea that working with a program state, like you would when you're working with doing something creative, like working with, like when you're working with Photoshop, or like when you're working with analyzing weather data, or like whatever examples that I was showing you before. We can extend these ideas onto all kinds of different programming environments that have different data representations. So this system that I'm showing right now, maybe this could be a start of something. So that is the main takeaway that I have for this paper. So that's all I want to say for now. Thank you.
Thank you for the talk. There's time for questions. Maybe I start with a quick one so that everybody can line up. Do you have an idea how you can transition the early CS education following these approaches, maybe to learn about, I don't know, computation, or some abstract thingy, to another kind of programming activity? Have you thought about, well, did you call it serious? I don't know if you called it serious programming, but
I could.
Have you thought about how to go from there if you have the chance to get the early CS students?
Do you mean how we could adapt empirical methodology?
You make up a goal, what they should learn. So like, I don't know, if you prepare them with Java and OO, or what would be an interesting learning goal?
So this is a question we keep asking ourselves, actually. How do we do similar studies with professionals? And it's hard. I think we could not show a completely new tool like this to a professional developer and ask him to do the same tasks like we've been doing in our existing studies. We could not ask him to do the same tasks in Alcott and React or Java or whatever, because it would obviously be too imbalanced. I don't think our system would fare really well. And also we have an issue with attitudes. Like I think many people just don't see programming as something that needs fixing. So I'm not optimistic that we could adapt this methodology so readily, but something that would maybe be worth considering is to see like how this could work for non-experts, like citizen developers, like people who are trying to do meaningful tasks with low-code or no-code tools, or even large language models, and see if this is something that, well, if it doesn't necessarily lead to like performance gains, at least improves their learning in some way of computer science. I'm optimistic that maybe that could be possible.
You're referring to the initial examples, right? Air traffic control and so on.
Yes.
Also, okay. Thank you. Let's have a next question.
Sorry. I tried out the Yogurt tool, and it was maybe the most satisfying to use of any visual programming environment I've ever tried.
Thank you.
At some point, I tried to make things that were a little bit more complex, and what I liked was the little sidebar area with the list of instructions and so on. So what I'm wondering is whether in any of your experiments you found how much people used that, and did they at any point start shifting or do different operations in the graph view versus in moving things around in the sidebar and so on?
I'm sorry.
Can you repeat the question, maybe?
Sorry,
You go please closer to the microphone.
Sorry. There's a little list in the sidebar of instructions of basically based on the things that you did, the manipulations you made of the graph. Yeah? The tracing area on the side, which you can.
I'm not sure if I heard you or understood you properly. So are you asking me if I observed some difference in when people start to do more complex tasks, if they prefer to use the...
Yes, but essentially yes. Is there a pattern of behavior when they start to look at that trace more often or less?
This is not something that we have observed in any empirical studies, like difference in behavior. Of course, as they start to do more complex tasks, they also grow more competent at using the system at the same time. So it's hard to as a confounding variable, I would say. But what we have observed, like with the new text editor that we have, this supports debugging. So once you start to do something that is more complex, you start to make more mistakes too. And that's one pattern that we see, at least, that people start to interact more with this small history bar that we showed here on the left in the application, that maybe they start to do more activities like dragging and dropping or rearranging existing operations to correct mistakes or like try to achieve something that they couldn't do in the first attempt. So.
I guess I'm wondering about the assumption here that even if you can visualize the state, whether it's graph or otherwise, whether that's always useful in order to do incremental programming. So I used to do like spacecraft simulations back in the day. And there's a very natural visualization. A lot of the new tools have that, where you have a little image of the spacecraft, and you can see it orbiting, and you can see it moving. But I'm not programming to get it to move a certain way. I'm programming the equations of motion and putting it into an environment, so it'll tell me how it's moving, so I can see if the design is right. So it doesn't really help me to be programming and watching it move, because I'm not sure if it's moving correctly or not. And I'd say there's a lot of situations like that, avionics, even banking, which has to conform to a lot of regulations and whatnot, where you can't just incrementally create based on, even if you have a very good representation of the state, because you don't know if it's right or not, because having it be right or not is usually something you have to look at over a lot of data and do a lot of tests to determine. And I have to, either implement the equations of motion of physics or implement the banking regulations or whatnot. Does that fit in there, or is there just a restricted range when this
I mean, I think
approach
this
would
might
work?
have a good point here. Like, maybe it's not going to be like the be-all or end-all of computer programming, like this way of thinking. But I guess what I wonder is, does it have to be? Like, maybe it can be helpful for a large number of tasks that we are not currently using this paradigm for right now. We could use this, we have tested this to do more complex applications, and we have not yet hit a roadblock. We have seen like how people can use this to build simple CRUD applications that they would struggle with in textual programming. Maybe eventually we're going to start hitting roadblocks where like we see diminishing gains or that this doesn't work altogether, but I think that's maybe okay.
To see it on more advanced CRUD operations. Also, you mentioned low code and things where you're incrementally adding. Yep. If somebody's already built a system, if you could visualize it in order to maintain it and operate on it, I think that would be a really good application also.
Sure, but my opinion is that there's actually it's surprising how far you can actually get with this. There were things in the beginning that we did not think was going to be possible using this paradigm, but we keep expanding on it and seeing more and more things that we can actually do. So I'm optimistic, I would say.
Push it as far as you can.
Thanks for thought-provoking talk. You asked two questions in your talk. One, whether this can be applied to professional development, and also whether graph-based visualizations are appropriate. So we actually do that in our company. So we're always trying to expose hidden state and create custom views of software. The thing is that we don't know in advance what states are going to be interesting. And as a consequence, it needs to be very cheap to add new views to existing objects of the state that we're exposing. As a consequence, very often we find that very simple views can get you a long way. Just simple tables and lists that dynamically update are very useful. Sometimes we want graph-based visualizations, and we have a nice little engine to do that. That's a bit more work. Or bar charts, or completely ad hoc visualizations, and they're more work. So I don't know, if there's a question there, my question to you is, have you considered the cost of building these views, and also the aspect of that you may need to add new views of hidden state while you're working on an application, instead of doing them all up front?
So thank you. This is a classical problem, I would say, with programming by demonstration systems, like Alcod is, like that. Creating custom visualizations is a time-consuming task, and it's not always worth it. But what we are hoping to achieve here is that this is something that is at least somewhat general purpose, like that you could imagine how for a programming task that you could build like customized like visualization of table or like some special data structure that you have for your system, and that this would be difficult. But we are hoping that if you build your entire system this way from the start, then, well, maybe this is something that can limit this cost that we're talking about here. So we will see, like, how far we can get.
Thank you.
Well, maybe one more question. Thinking of I think the comment on simulations and maybe tweaking simulations with this kind of programming approach. And what do you think, as you just said, like building it from the ground up versus just using it where it fits, right? So like a domain-specific configuration language thingy, like, what are your thoughts on that? So it sounded to me like you don't want to give up too early, so it's not just the domain-specific configuration approach where nodes and edges fit well, but maybe to construct more out of it. So I'm curious, why do you go this way? Because on the domain-specific language area, people are like, okay, that's fine. It works perfect for this use case and maybe some more, but we will never try to build, I don't know, an entire operating system, whatever, big. Yeah, so maybe you can share some more thoughts on that. Where, when, how do you push your boundaries? And yeah.
I'm sorry, I find this a bit broad. Can you
it's
maybe
very broad. So my first, well, when I see the system, I think of a very specific outside the education context. Sure, use it when you want to configure a small simulation or teach about linked lists and so on, or some kind of smaller problems. And I'm having a hard time to find the transition to scale this thing up.
Yes. And
I'm ending up with, oh, at some point I want to use my keyboard and be more productive, less drag and drop, whatever. But this could be a fallacy, I know. So like, this is what we learned about, and so this is what we try to go there. So, what are your strategies to not fall into this fallacy?
So there's a lot of unknowns here. We don't know yet. But something that we observe very often, this is remarkable, I think, is that when we show this to people who have less technical skills, that are trying to build software but have never taken like any computer programming courses, are just trying to scrape things together with using ChatGPT or like Excel or like low-code environments. When they see our tool, they see possibilities that experts, well, don't necessarily see. They see limitations. They think, okay, well, I could never use this to build my spaceship at my company. But I don't know. Like, I guess just, the future will tell us, like, if that is ever going to be possible. But I think my point is that even if it's not, maybe there is something to it, like to this thinking that we could try to make computer programming resemble creative applications more, that this could be helpful in the end. So.
Thank you. Let's thank the speaker. We have one more question. Sorry.
Thank you. Yeah, thank you so much for the super interesting talk. So one line of research that I'm interested in is using kind of similar like visualization techniques to extend existing languages. Sorry. So I'm wondering, from your experience building Algot, you know, kind of designing this own standalone system to kind of allow people to visualize state, do you think that there's anything to be learned from that to apply to like existing languages for, you know, building tools for languages that people already use? And yeah, just generally, how do you feel about that whole line of research? Do you think it could be fruitful?
So I just want to be clear that building this has been a collaborative activity with my students and me. So my experience and theirs might differ. But to get back to your question, so are you asking like, sorry, I was a bit distracted. Are you asking like the difference between using this like as an add-on to existing languages or like?
Yeah, exactly. Okay. Yeah, generally like, do you see promise for applying similar techniques to allow people to visualize state in existing languages? I guess especially for like professional developers. And are there any like learnings specifically that you've taken from developing this language that you think could be helpful for existing languages?
I hope so. I mean, it would be quite a lot of work, like integrating a new visual language with existing technology is a lot more difficult task than to, well, build something from the start with it, like, or like to build a tool that is intended to be used that way. Maybe that's something that we could look into the future, but like it means that the way that we represent data, like I mean, it has to algo is graph-based, so that's what we want limitation from the beginning, and also integrating it with existing code is also would be a challenge because the computational model is very different. I think it's useful and intuitive, but well, we don't have a lot of nesting, for example, like a way you do in a typical imperative textual programming language. The query system works differently, so it's maybe something worth exploring. It could be maybe that could be the killer application in the end. So.
Thank you so much.
Let's thank the speaker again. And this brings us to the conclusion of this year's Onward. It's not on, right? Yet? No, it's on. So I added the 23rd. So it's the 23rd Onward we had this year, and we are now about to conclude. Jonathan and I took care of collecting all your submissions and making sure to have nice proceedings and also good talks. And I think we managed to find a good schedule. I think it was fun from all the way through. I liked it. We had very fruitful discussions during the hallways, here, after the talks, and I think 1 or 2 times I had to warm you up a little bit with an intermediate question, but usually people line up for themselves. So let's have a look again. So yeah, we had all these beautiful papers, all about programming systems. What do we have here? Yeah, natural language, and well, you can maybe take a look again in the video if you discovered something new or are still looking for, I don't know, the one paper that's about object, yeah, I know, yeah, or debuggers. And then we had a lot of essays, more about design and how maybe languages work. And we had a beautiful keynote. And I think I have to watch this at least 3 more times or read the transcript, because I found so many interesting aspects in it and historical bits of information to put things into perspective, into context, to kind of be a little bit more aware when we read today's information about the progress in the LLMs and the AI. And I would encourage everybody in the room to do so again. And yes, and maybe check out the other keynotes he had over the years. I think most of them are on YouTube or on his website, dreamsongs.com. He has a lot of other interesting texts collected over the years and essays. There are many interesting, well, there are a lot of interesting events coming up. We picked out a few. So there's a programming conference happening in Prague next June. And unfortunately, the submissions for that event are closed because they have this 3 deadline journal programs. So the next deadline is in February, but it's for 2026. So they're collecting from February, June, and 1st of October. And they already did that for that conference. But there will be the next iteration of the Program Experience workshop there. and submissions usually happen around mid-January. The workshop submissions themselves are still running to mid-December or something, right? And then the workshop will be up on the page. Then we have next year's Onward happening together with next year's Splash. Submissions usually happen until April 2025, and there will be, I think, another live next year. Submissions are usually in summer, and yeah. Do you want to add anything?
Thanks for coming. You're welcome. Let's just keep the ball rolling. Those other events there are other opportunities, and I think it's great that everybody is coming up with weird new ideas outside the mainstream, because the mainstream is taking care of itself. So just keep it up. It's great to see it.